Hubble was pointed at what looked like nothing, a dark, empty patch of space. No stars, no galaxies, just blackness. But when the images came back, that emptiness exploded with light, thousands of galaxies where nothing was supposed to exist. What Hubble found changed how we understand the universe. The patch of nothing. The universe is vast, far larger than anything our minds can easily imagine, stretching beyond the edges of what we can see, full of galaxies, stars, nebulae, and cosmic explosions. Everywhere we look, there is light, there is energy, there is something. And yet in the mid-1990s, astronomers began to notice something strange, something almost impossible to describe. There were areas of space so empty, so profoundly silent, that they seemed to exist outside the natural laws of the cosmos, patches of nothing where even the faintest glimmer of a star or galaxy seemed to vanish. These regions were not just dim or hard to observe, they were statistically barren. If the universe was a tapestry woven with galaxies, these patches were holes, gaps, where the threads of light and matter appeared to have never been woven at all. Astronomers call these regions dark patches of space. The term itself sounds simple, almost casual, but in reality, defining a dark patch is one of the most precise and rigorous processes in modern astronomy. A dark patch is not merely a place where you cannot see anything with your eyes. The human eye is limited. It can only detect a tiny fraction of the electromagnetic spectrum. When astronomers talk about a dark patch, they mean a region where even the most sensitive instruments, designed to detect light across every conceivable wavelength, detect nothing beyond the background noise. It is a place where galaxies do not appear, where starlight is absent, and where the faint whispers of distant radiation seem to vanish into the void. These areas are rare. The universe is a crowded place, and even the most remote regions of intergalactic space are normally filled with faint galaxies, clouds of gas, or diffuse light from stars too far away for us to see individually. To find a truly empty region, astronomers have to look carefully, strategically, and with instruments capable of revealing the faintest glimmers of light that the cosmos allows to reach us. But there is more to the concept of nothing than meets the eye. Darkness, as it turns out, is not a single, simple phenomenon. There are layers of emptiness, layers that astronomers must peel back one by one to understand what they are truly seeing. Optical darkness is the first and most intuitive layer. In visible light, the patch appears black. A telescope trained on the patch sees little to no stars, no distant galaxies, no glow of nebulae. Just an apparent void that stretches in every direction. But optical darkness is only one dimension. When astronomers turn to infrared observations, using detectors sensitive to longer wavelengths, the scene can change dramatically. Infrared light can penetrate clouds of dust and gas, revealing stars hidden behind cosmic veils or early galaxies too faint to appear in visible light. An empty patch in the optical might glow in the infrared, hinting at objects that optical telescopes cannot detect. The absence of infrared light, however, is far more puzzling. It suggests that even the warm, faint energy of distant stars and galaxies is missing, that the region is not only visually empty, but physically devoid of the sources that normally fill the universe. Then there is radio silence. Radio waves, with their long wavelengths, can traverse distances and obstacles that optical and infrared light cannot. They reveal phenomena entirely invisible to the human eye. Pulsars spinning with clockwork precision, jets of energy expelled by black holes, clouds of hydrogen gas drifting between galaxies. In a patch of radio silence, these signals are absent as well. The region shows no emissions, no background radiation beyond what is expected from the cosmic microwave background, the afterglow of the Big Bang itself. This is a level of emptiness almost unimaginable, a region where the universe seems to have done nothing at all. The combination of optical darkness, infrared emptiness and radio silence creates a puzzle that astronomers cannot ignore, a location that challenges every assumption about how matter and energy are distributed across space. The particular patch that captured the attention of astronomers and would later become the focus of the Hubble Space Telescope's gaze was extraordinary even by these rare standards. Its location was chosen with meticulous care. Astronomers scanned the sky for areas where foreground stars from our own Milky Way would not interfere with observations, where cosmic dust would not scatter or absorb light, and where the brightness of nearby galaxies would not contaminate the view. They calculated the probability of finding galaxies in different regions of the sky, combining models of galaxy distribution with observational data from previous surveys. This patch emerged as statistically empty, a candidate for what they called a deep field, a region where the telescope could peer as far back in time as possible without interference. Previous instruments had either glanced briefly at this region or ignored it entirely, as most telescopes were tasked with surveying brighter objects, the ones that could provide immediate data about stars, planets, and galaxies closer to home. In this region, previous observations had detected nothing: no catalogued stars, no known galaxies, no unusual sources. It was as if nature itself had forgotten this part of the sky. This emptiness was not an accident. In the world of observational astronomy, looking at nothing is an intentional and deliberate strategy. Astronomers seek these voids because the absence of foreground clutter allows telescopes to detect the faintest, most distant galaxies. In crowded fields, light from nearby stars washes out the faint signals from the early universe. In dark patches, every photon matters. Every tiny signal can be traced back across billions of light years. By targeting the void, astronomers are essentially setting a cosmic stage, removing all distractions so that the earlier structures of the universe can be illuminated. It is a hunt for the faintest whispers of light, the delicate fingerprints of the first galaxies and stars, and the patch chosen for this observation was among the best in the sky. Into this void, astronomers trained the Hubble Space Telescope. Hubble had been orbiting Earth for decades, a sentinel of the cosmos, capable of seeing farther and clearer than any telescope that came before it. Its position above Earth's atmosphere allowed it to avoid the blurring effects of air, to detect faint ultraviolet light that never reaches the ground, and to collect data across visible and infrared wavelengths with unprecedented sensitivity. The patch of nothing became the target of what would be one of Hubble's deepest and longest observations, an exposure that required days of uninterrupted focus, stacking hundreds of individual images to reveal the faintest possible sources. The coordinates of the patch were carefully logged, an area only a few arc-minutes across, roughly 1/10 the size of the full moon as seen from Earth. Its galactic latitude placed it far from the plane of the Milky Way, reducing interference from stars, gas and dust in our own galaxy. Foreground stars were sparse, almost non-existent, and the cloud of interstellar dust that often clouds observations was virtually absent. It was a window into the universe as it had never been seen before, a place so empty that astronomers dared to hope they might glimpse the very first light from the earliest galaxies. The patch of nothing was a paradox. To the naked eye it was invisible, a blank space in the sky. To telescopes that surveyed the universe for decades, it was unremarkable, one small region among billions. Yet to Hubble, with its extraordinary sensitivity and capacity for deep-field imaging, it was a treasure. It offered the possibility of seeing beyond the universe we know into a time when galaxies were just forming, when stars were igniting for the first time, when the cosmos itself was young and chaotic. Every detail of this patch had been calculated, measured and confirmed. Its coordinates, its size, its orientation, its galactic latitude, and the absence of foreground light. It was carefully chosen to be the quietest, emptiest, most pristine observation window possible. As Hubble turned its gaze to the patch, astronomers held their breath. This was a leap into the unknown, a search not for what was expected, but for what might be impossible. They trained their most precise instruments on a region defined by absence, a patch where the universe seemed to have left no trace. For days, Hubble collected photons, stacking images with surgical precision, counting each bit of light that managed to escape the darkness of space and reach its detectors. The process was painstaking, the analysis meticulous. Every potential source had to be verified, every faint blur distinguished from noise, cosmic rays, and instrumental artifacts. This was science at its most exacting, where even a single misinterpretation could rewrite the story of the universe. And yet, as the first processed images appeared, astronomers noticed something curious. The patch was not entirely empty. Something faint flickered in the darkness. The light was so subtle, so delicate, that at first it could easily have been dismissed as noise or a technical error. But it was real, and it was structured, not random. Even in the darkest part of space, where the statistics predicted nothing, the universe had left traces. The faintest glimmers of galaxies that existed when the cosmos was young, still forming, still chaotic. The patch of nothing, so carefully chosen for its emptiness, was about to reveal secrets that would challenge everything astronomers thought they knew about how the universe formed and evolved. The observation that shouldn't work. Hubble was unlike any telescope that had come before. Floating above the distortion of Earth's atmosphere, it could capture ultraviolet light, visible light, and near-infrared wavelengths, detecting photons that had travelled for billions of years, crossing the void, escaping the gravity of galaxies, and surviving cosmic dust and gas clouds that would have stopped lesser telescopes. Every image it collected was not a snapshot, but a layer of reality, stacked, calibrated, and corrected to reveal the faintest hints of cosmic structure. Hubble's instruments were both sensitive and delicate. The Wide Field and Planetary Camera, the Advanced Camera for surveys, and later the Wide Field Camera 3 were capable of detecting single photons, each one a tiny messenger from the edge of the observable universe. But seeing light was not enough. The telescope had to separate real signals from noise, from cosmic rays that slammed into its detectors, from thermal variations in the instruments, from the subtle electronic interference that comes with any sophisticated sensor. The images were processed with extreme care, each photon counted, each faint dot measured, and each potential object verified across multiple exposures and wavelengths. This was a level of observation that turned patience into a scientific weapon, a precision that made the impossible detectable. For the first time, astronomers could study the patch of nothing in extraordinary detail. They stacked hundreds of individual exposures, a technique that allowed extremely faint light to emerge from the background. The process was like tuning a radio across the static of space, slowly raising the volume until the first whisper of a signal could be heard. At first, the images seemed empty, confirming what statistical models had predicted. But as the exposure time accumulated, something subtle appeared. Faint smudges, barely distinguishable from the background, began to take shape. They were not bright, and they were not obvious, but they were consistent, appearing in multiple frames and multiple filters. They were small, distant galaxies, some so faint that they were nearly invisible even with Hubble's incredible power. The first sign that something was wrong came in the distribution of these galaxies. The patch had been chosen for its emptiness, a region where only a handful of galaxies were expected to appear. Statistical models, based on decades of observations and simulations, suggested that this corner of the sky would reveal only a small number of faint objects, scattered randomly across the frame. Instead, the galaxies were too many. They clustered in ways that should have been impossible. Where theory predicted scarcity, there was abundance. Where simulation showed disorder, there was structure. The faint smudges of light, which should have been random, hinted at a surprising order in the darkness. They were not mere dots. Some displayed shapes, faintly elongated or clumpy, suggesting that even at this extreme distance, galaxies had already begun to form distinct structures. Colours offered another clue that defied expectation. Hubble observed the patch through multiple filters, each designed to detect light at specific wavelengths. By comparing the intensity of light in different bands, astronomers could estimate the age, composition, and distance of the galaxies. The results were astonishing. Some galaxies emitted light that implied they were older than models suggested possible, forming stars earlier than expected after the Big Bang. Others were so faint that their existence should have been invisible at this stage of the universe. And yet there they were, faint but unmistakable, tiny beacons from the distant past. The combination of their colours, shapes, and distribution suggested a universe that had begun building complex structures far earlier than anyone had imagined. The process of confirming these findings was painstaking. Astronomers had to rule out every possible source of error. Could the faint smudges be noise? Could they be cosmic rays that mimicked the appearance of galaxies? Could instrumental defects in the detectors have produced false signals? Each possibility was tested, retested, and eliminated. Independent teams reprocessed the data using different pipelines, different software, and different calibration techniques. The faint galaxies remained. They were real. They were numerous. They were structured. And they were impossible, at least according to the prevailing models of cosmology. One of the first surprises came from the sheer number of galaxies detected. In a patch of sky only a fraction of the size of the full moon, the number of galaxies far exceeded predictions. Cosmological simulations based on the known physics of cold dark matter and hierarchical galaxy formation suggested that this many galaxies should not exist at this distance. Yet there they were, faintly glowing against the darkness, each a testament to the universe's ability to form structures with astonishing efficiency. Their luminosity was another puzzle. Some were brighter than expected for their distance, suggesting that they contained surprisingly massive amounts of stars, already forming in large numbers despite the short time since the Big Bang. Others were so faint that they defied detection until Hubble's longest, deepest exposures revealed them. This combination of abundance and diversity in a supposedly empty region challenged assumptions about how quickly matter could coalesce into galaxies and how efficiently star formation could occur in the early universe. Even more striking was the apparent age of some of these objects. By analysing the light they emitted, astronomers could estimate the stellar populations within these galaxies. Some contained stars that appeared older than expected, implying that star formation had begun almost immediately after the first galaxies formed. These were not young, chaotic collections of gas. They were organised with hints of spiral arms, clumps, and other structures that suggested a history of assembly. The early universe, long assumed to be a slow, chaotic place, was revealed in these images as far more efficient and far more ordered than anyone had imagined. Every step of this discovery required meticulous validation. Astronomers cross-checked observations against previous surveys and catalogues. They compared the faint signals to control fields in other parts of the sky, ensuring that what they were seeing was not a fluke of measurement or an anomaly in one specific instrument. The faint galaxies persisted, confirming that Hubble was detecting real, previously unseen structures. Even experts who had spent decades observing the universe were surprised. The patch of nothing carefully chosen for its emptiness was revealing a richness of detail and structure that defied explanation. As the days turned into weeks, the image of the patch solidified. The data revealed hundreds of faint galaxies, each a snapshot of a time billions of years in the past. Each galaxy was a complex system of stars, gas, and dust, many forming stars at rates far higher than previously thought possible. The distribution of galaxies suggested that large-scale structures, such as filaments and clusters, were already emerging, hinting at the cosmic web that would later dominate the universe. And yet, all of this appeared in a patch of sky that had been predicted to be nearly empty, a corner of the cosmos where theory said almost nothing should exist. The tension between observation and theory became impossible to ignore. Astronomers had expected to see a handful of faint dots, maybe a dozen small galaxies scattered across the field. Instead, Hubble revealed hundreds, each challenging the timelines of galaxy formation, the efficiency of star formation, and the evolution of structure in the early universe. Every photon captured by the telescope carried information that contradicted long-held assumptions. Every faint glow was a piece of a puzzle that cosmologists had never expected to encounter. Hubble's observation transformed the patch of nothing from a blank canvas into a window into the early universe. It revealed that the universe had been forming structures far more quickly than previously understood. It showed that galaxies could assemble, mature, and begin forming stars almost immediately after the first billion years. It hinted that the cosmos was not a slow, chaotic progression from nothing to something but a place capable of astonishing efficiency and order from the very beginning. The dark patch that had been chosen for its emptiness became one of the most productive discoveries in the history of deep-field astronomy, a region where the impossible had begun to take shape. The many shades of nothing. The darkness of space is deceptive. To the naked eye, the night sky can appear deep and empty, a velvet expanse punctuated by the sparkle of stars, the faint smudge of the Milky Way, or the occasional flash of a distant planet. But the truth is that what we see is only a fraction of reality. The universe is alive with light across wavelengths far beyond human vision, from the shortest ultraviolet bursts to the longest radio waves. When astronomers speak of a patch of nothing, they mean more than just an absence of visible stars. They mean a silence that stretches across the spectrum, a void that persists even when the most sophisticated instruments peer into realms invisible to us. To understand what Hubble revealed, it is essential to explore the difference between optical darkness, infrared emptiness, and radio silence, three distinct yet interconnected dimensions of cosmic emptiness. Optical darkness is the first layer of emptiness, the kind we intuitively understand. It is what we see when we look up at the sky and find nothing but blackness, the absence of light in the wavelengths that the human eye can detect. For centuries, astronomers relied on optical observations, telescopes that collected visible light and recorded stars, galaxies, and nebulae. A patch of optical darkness is one where even these observations, across decades and generations, detect virtually no sources. The optical light from galaxies, the glow of distant stars, the faint emissions of interstellar gas, all are missing or so faint as to be indistinguishable from background noise. Optical darkness is not merely the absence of bright objects, it is the absence of detectable light altogether. It is a profound kind of emptiness, because visible light is the first way humans have measured and mapped the cosmos. The absence of optical signals in a region of space immediately marks it as unusual, a candidate for deeper study. However, optical darkness does not necessarily mean true emptiness. Many cosmic objects emit light outside the visible spectrum, and some of the most intriguing and important structures in the universe are invisible to optical telescopes. Dust and gas, for example, can obscure stars and galaxies in visible light, scattering or absorbing photons so that no signal reaches Earth. Optical darkness can mask a hidden universe behind these veils, giving the illusion of emptiness, where energy and matter may be abundant. It is here that infrared observations become essential, revealing a layer of emptiness or presence that optical telescopes cannot detect. Infrared light penetrates the cosmic fog in ways visible light cannot. It is longer in wavelength and capable of passing through clouds of dust, unearthing stars, proto-galaxies, and other hidden sources that would otherwise be invisible. Infrared observations reveal the heat of celestial objects, the faint warmth of stars forming in shrouded regions, and the glow of distant galaxies redshifted into the infrared by the expansion of the universe. When a patch of space shows infrared emptiness, as well as optical darkness, it is extraordinary. It indicates that the absence is not due to dust or obscuration, but is intrinsic to the region itself. No warm stars, no hidden galaxies, no subtle sources of heat emerge to betray the darkness. Infrared emptiness suggests a void that persists even when the universe is observed with instruments capable of peeling back layers of obscuring material. It is emptiness confirmed across a range of light that humans cannot see, a stronger statement about the nature of the region than optical darkness alone could provide. But the universe does not reveal its secrets in visible or infrared light alone. Radio waves carry signals from entirely different phenomena, probing structures that neither optical nor infrared light can detect. Radio astronomy is the study of the longest wavelengths, a window into the cosmos that reveals hydrogen clouds, spinning neutron stars, jets from black holes, and even the diffuse whisper of cosmic radiation. A patch of radio silence is a region where none of these signals are present beyond the expected cosmic background. It is a void in a dimension that measures entirely different processes: the movement of charged particles, the interaction of magnetic fields, the faint hum of hydrogen gas that traces the skeleton of the universe. When a region exhibits radio silence as well as optical darkness and infrared emptiness, it is a true anomaly. The silence suggests not merely the absence of stars and galaxies, but the absence of matter emitting or interacting in detectable ways. It is a statement about the physical universe itself, not just about what is visible. The combination of these three forms of emptiness is what made the patch Hubble observed so remarkable. Optical darkness alone could have been explained as dust or distance. Infrared emptiness alone could have been accounted for by faint, cold objects falling below detection limits. But the patch showed all three. No visible stars, no hidden infrared sources, no radio emissions. Just a quiet expanse stretching across billions of light years. The implications were profound. A region that is dark across these three bands is statistically almost impossible. A location where the density of detectable galaxies and matter is far below expectations. The universe, it seemed, had created a blank canvas, a place where the normal rules of cosmic abundance were suspended. Astronomers did not stumble across such patches by accident. They deliberately target regions expected to be empty because the emptiness itself is a powerful tool. By pointing telescopes at areas where foreground stars are absent, where dust clouds are minimal, and where previous surveys showed few or no galaxies, astronomers create a clean window to the early universe. In these regions, every photon detected is a rare treasure, a signal that has traversed billions of years without interference. In crowded regions, light from nearby stars washes out these faint signals, obscuring the earliest galaxies and the structures that formed them. By seeking out the emptiest regions, astronomers can detect the most distant and oldest objects, glimpsing a universe as it was billions of years ago. The patch Hubble observed exemplified this strategy. Its coordinates placed it far above the plane of the Milky Way, minimizing interference from stars, gas, and dust. The size of the field was only a few arc-minutes across, tiny compared to the sky as a whole, but vast enough to capture hundreds of faint objects if they existed. The absence of foreground stars and dust created near-perfect conditions for long exposures. Previous surveys had glanced at the region, noting its lack of bright objects, but none had investigated it in depth. Hubble, with its unprecedented sensitivity, was capable of revealing structures that had never been seen, capturing photons that had travelled for over 13 billion years. Every detail of the observation was calibrated with care. The telescope's instruments were selected to maximise sensitivity to both visible and near-infrared light, ensuring that faint red-shifted galaxies could be detected. Long exposure times allowed the faintest light to accumulate, while stacking hundreds of frames reduced the influence of cosmic rays and instrumental noise. Radio silence was confirmed by cross-referencing with the deepest radio surveys, showing that the patch was devoid of hydrogen clouds, pulsars, and other common sources of radio emissions. This was not a simple blank spot. It was a carefully verified absence, confirmed across multiple wavelengths, each reinforcing the others. This multi-dimensional emptiness transformed the patch from a statistical curiosity into a profound observational opportunity. Optical darkness, infrared emptiness, and radio silence together defined a region where the universe itself seemed to have been suspended. It was the perfect laboratory for exploring the earliest galaxies, the formation of the first stars, and the processes that built the large-scale structure of the cosmos. By studying this patch, astronomers could see farther, older, and fainter than ever before, pushing the limits of human observation into the first billion years of cosmic history. As Hubble began its deep exposures, photons that had travelled for billions of years began to accumulate on the detectors. Each photon was counted, calibrated, and analysed to ensure that it represented real light from distant galaxies rather than noise or instrumental artifact. In the optical band, the field initially appeared as expected, a near-perfect darkness punctuated by the rare, faint galaxy. In the infrared, the emptiness persisted, confirming that dust and obscuration were not masking hidden sources. In the radio, the silence held, verifying that the absence extended to the distribution of hydrogen gas, pulsars, and other emissions. The patch of nothing was not simply empty in one way, it was empty in every measurable way, a phenomenon that both challenged theory and created an unprecedented opportunity for discovery. For astronomers, this emptiness was not discouraging but exhilarating. The lack of bright foreground objects meant that Hubble could detect the faintest and most distant galaxies. Every photon that reached its instruments could be traced back to the earliest stages of the universe, revealing structures that had formed when the cosmos was only a fraction of its current age. The patch became a window into the unknown, a place where nothingness itself illuminated the origins of everything. It was in this profound void, defined by optical darkness, infrared emptiness, and radio silence, that Hubble would begin to detect galaxies that should not exist, objects that would force astronomers to rethink everything they knew about the early universe. The patch designed to reveal the universe. Even within the vastness of the cosmos, astronomers do not stumble upon emptiness by accident. Every observation is carefully planned, every telescope pointing is deliberate, and every patch of sky has a story before the first photon ever arrives at a detector. The particular region that would become known as the patch of nothing was selected not because it was empty in a mysterious, mystical sense, but because calculations, observations, and statistical predictions had all indicated that this was one of the quietest, least cluttered places in the sky. It was a blank canvas designed with intention, a cosmic window chosen to give humanity the clearest possible view of the earliest galaxies. In a universe dominated by matter, light, and energy, finding a region that appeared statistically empty was like finding a perfect lens through which to glimpse the origins of everything. Astronomers began by examining previous surveys of the sky. For decades, ground-based telescopes had mapped large swaths of the heavens, cataloguing stars, galaxies, nebulae, and other cosmic objects. Wide-field surveys revealed patterns of galaxy clustering, cosmic filaments, and dense regions filled with light. But hidden between the crowded patches of the universe were gaps, regions where fewer galaxies appeared than statistics would predict. These gaps were not absolute voids, but they were statistically significant. They were places where the number of observable galaxies fell below the expected mean, where the probability of finding luminous matter was lower than anywhere else. By carefully analysing these gaps, astronomers could identify areas where a deep observation would be least contaminated by foreground objects, the light from stars in our own Milky Way, or nearby galaxies whose glow might overwhelm faint, distant sources. This patch of sky, far above the plane of the Milky Way, was one such location. Its galactic latitude placed it away from the dense disk of our galaxy, where stars, gas, and dust are concentrated. This position alone reduced interference from foreground stars, which could obscure faint, distant galaxies. The lack of dust minimized absorption and scattering of light, ensuring that photons from faraway objects would reach Earth and its orbiting telescopes with minimal distortion. Previous observations, including surveys conducted in optical, infrared, and radio wavelengths, had noted the sparsity of detectable objects in this field. Unlike other regions where faint galaxies appeared consistently across surveys, this patch remained remarkably empty, a statistical anomaly that hinted at the possibility of a nearly pristine view of the distant universe. Yet the emptiness of the region was not simply a curiosity. It was a strategic choice. In cosmology, observing nothing can be just as important as observing something. Dense fields of stars and galaxies are beautiful and scientifically valuable, but they make it difficult to detect the faintest objects. Light from nearby sources can overwhelm the detectors, drowning out signals from the earliest, most distant galaxies. By targeting a patch of sky that appeared empty, astronomers could reduce this contamination to a minimum. In effect, the statistical emptiness of the field acted as a filter, allowing Hubble to detect light from galaxies billions of light-years away that would otherwise be invisible. This is the principle behind deep field astronomy. By carefully selecting the quietest regions of space, astronomers can maximize the telescope's sensitivity and push the boundaries of what can be observed. Previous instruments had glimpsed this patch, but never with the depth or precision required to reveal its secrets. Ground-based telescopes had surveyed the area, noting a lack of bright stars or obvious galaxies, but the limitations of Earth's atmosphere prevented them from detecting the faintest objects. Even sophisticated infrared and radio surveys had registered little activity. In optical wavelengths, there was nothing but darkness. In infrared, there were no hidden sources to illuminate the field. In radio wavelengths, there was silence. Each observation hinted that this was not just a visually empty region, but a place where the density of luminous matter was extraordinarily low. But none of these observations could penetrate the limits of faintness that Hubble would later overcome. The Hubble Space Telescope was uniquely suited to turn statistical emptiness into discovery. Launched into orbit in 1990, Hubble avoided the blurring effects of Earth's atmosphere, allowing it to detect photons with unmatched clarity. It carried instruments designed to capture light across the visible and near-infrared spectrum, each capable of detecting incredibly faint sources. Its detectors were sensitive enough to register single photons, and its orbit allowed for long, uninterrupted exposures that could stack hundreds of images to reveal what would otherwise remain invisible. Hubble was not simply a telescope, it was a precision instrument for mapping the cosmos at the edge of perception, a tool that could transform the carefully chosen statistical void into a window onto the earliest epochs of the universe. In planning the observation, astronomers calculated every detail of the field. The patch was only a few arc-minutes across, roughly 1/10 the diameter of the full moon as seen from Earth. Despite its small size, it was large enough to capture a representative sample of the universe's early galaxies, while small enough to allow long exposures without interference from brighter objects. The absence of foreground stars and interstellar dust ensured that faint galaxies billions of light-years away would not be washed out. The galactic latitude was optimal for minimizing contamination from our own galaxy, and prior surveys had confirmed the statistical emptiness of the field. Every parameter had been measured, tested, and cross-checked. There was no mystery in its selection. It was a deliberate, calculated choice to maximize the likelihood of discovering the faintest and most distant structures in the cosmos. This careful selection paid off in ways that would astonish astronomers. When Hubble began its long exposures, it was looking at a region that, according to statistical predictions, should have contained almost nothing. Every photon captured from this patch carried information from a galaxy, a star, or a structure that had formed billions of years ago. As the images accumulated, the darkness began to yield faint points of light, subtle smudges that hinted at galaxies previously unknown and unseen. The field that had been chosen because it was empty turned out to be a goldmine, revealing structures and populations that defied expectations. The statistical void had become a window into the early universe, a place where the absence of clutter allowed the first whispers of cosmic history to emerge clearly. Hubble's observation of this patch marked the beginning of a new era in cosmology. For the first time, astronomers could study the faintest galaxies in the quietest regions of the sky, seeing the earliest stages of galaxy formation and evolution. The telescope's sensitivity, combined with the careful selection of the field, made it possible to detect galaxies that had formed only a few 100 million years after the Big Bang, structures so faint and distant that they had been invisible to every instrument that had come before. In choosing a region that appeared statistically empty, astronomers had created the conditions necessary to witness the universe in its infancy, to see the light from the first galaxies and the beginnings of cosmic structure. As the photons from this patch accumulated on Hubble's detectors, the images revealed a subtle but profound truth. The emptiness of the field was only apparent. Beneath the darkness lay a hidden population of galaxies, each a record of the universe's earliest epochs. The careful selection of the patch, informed by previous observations, statistical analysis, and an understanding of cosmic structure, had made it possible to see these galaxies for the first time. The instruments that had previously observed the field had detected nothing, not because the galaxies were absent, but because they were beyond the reach of less sensitive telescopes. Hubble transformed statistical emptiness into discovery, turning a patch of nothing into a field of first light. By deliberately targeting a region of apparent nothingness, astronomers were able to see what no one had ever seen before. The patch became a laboratory for understanding the early universe, a controlled environment in which every faint photon could be traced, analyzed, and interpreted. Hubble's instruments, calibrated for maximum sensitivity and precision, captured images that revealed the unexpected abundance of faint galaxies, their distribution, their color, and their structure. The patch that had seemed empty on paper became one of the most detailed and profound views of the distant universe ever recorded, a testament to the power of careful planning, precise instrumentation, and the audacity to look into nothing and discover everything. Why Hubble was aimed there at all. Even the most advanced telescopes must choose their targets carefully. Space is vast, and every second of observation is precious. The universe is a crowded place, filled with stars, galaxies, gas clouds, and the faint glow of countless cosmic events. Yet, paradoxically, some of the most important discoveries come from looking where there seems to be nothing at all. When astronomers first proposed aiming the Hubble Space Telescope at a tiny, empty patch of sky, the idea seemed almost counterintuitive. Why waste the most powerful eye humanity had in orbit, staring at a region that appeared completely barren? The answer lies in the strategy of deep field astronomy, a method designed to uncover the faintest, most distant galaxies, to look further back in time than ever before, and to reveal the early universe in ways that ordinary surveys could never achieve. Deep field astronomy is not about capturing a wide panorama of the sky. It is about precision, patience, and pushing the limits of detection. Unlike wide-field surveys that map millions of stars and galaxies, deep-field observations focus on a tiny patch of sky and observe it for days, sometimes weeks, accumulating faint photons that have travelled for billions of years. The Hubble Deep Field, first captured in 1995, was the proof of concept. This new deep field revealed galaxies forming within the first 500 million years of the universe, providing a window into the epoch of reionization, when the first stars ignited and transformed the cosmos. Each of these deep fields relied on careful planning, not just random pointing. The patches selected were chosen for their emptiness, their lack of foreground interference, and their ability to reveal the faintest galaxies possible. That strategy became central to the planning of the patch that would later astonish astronomers with its apparent statistical emptiness. Astronomers understood that to capture light from the earliest galaxies, they could not simply aim Hubble anywhere. They needed the cleanest, quietest region of sky, free from distractions, where every photon counted. The criteria for choosing such a region were precise. Low zodiacal light was essential. Zodiacal light comes from sunlight scattered by dust particles in the plane of the solar system. Even faint, diffuse light can overwhelm the signals of extremely distant galaxies. By choosing a patch far from the plane of the solar system, astronomers minimize this interference, ensuring that Hubble's detectors would not be swamped by foreground brightness. Minimal interference from the Milky Way was equally critical. Our galaxy is filled with stars, gas clouds and dust lanes that can obscure the light of distant galaxies. The dense star fields of the galactic plane are a visual maze, making it difficult to distinguish faint background objects from nearby stars. By selecting a region at a high galactic latitude, astronomers avoided this clutter, creating a nearly transparent window through which Hubble could peer into the depths of space. Instrument calibration was another reason for the careful choice of target. Hubble's cameras and detectors required stability and predictability. Observing a region that was too bright, too crowded, or too variable would risk saturating the sensors or complicating the data analysis. Empty regions provide a baseline, a place where faint light can be separated from instrumental noise with confidence. The patch was small enough to allow repeated exposures without introducing distortions from telescope motion, yet large enough to contain hundreds of potential galaxies. Every element of the observation was optimized for the telescope's capabilities. Once the region was selected, the next question was exposure time. Long exposure times are the key to deep field discoveries. Faint photons from galaxies billions of light years away arrive at Earth sparsely, often as few as a handful per hour per detector pixel. Capturing these photons requires hours, even days, of continuous observation. In the past, telescopes would scan the sky quickly, detecting only the brighter, nearer objects. Hubble's deep field strategy was different. It traded breadth for depth, aiming for the faintest and most distant sources, even if that meant committing weeks of observation to a single, tiny field. Astronomers had clear expectations. Based on statistical models, this particular patch should contain very few galaxies, mostly sparse background objects, each one faint and isolated. They anticipated a gradual noise floor, the inevitable accumulation of background signal from the telescope itself and from diffuse cosmic light. They expected nothing statistically abnormal, no surprises, only faint galaxies, and the satisfaction of extending observational limits further than ever before. That expectation, grounded in decades of survey data and cosmological models, was essential to justify the long exposure time. A patch of apparent emptiness offered a clean environment to test the limits of Hubble's instruments, to see the first galaxies without interference from foreground clutter, and to collect data that could refine our understanding of galaxy formation. Previous deep fields had proven the strategy. The Hubble Deep Field, with its 10 days of observation, had revealed hundreds of galaxies in what had seemed to be a dark patch of sky. The ultra-deep field went further, capturing the faintest, reddest galaxies that existed when the universe was still forming its first stars. These observations demonstrated that targeting nothing can produce something extraordinary, that statistical emptiness is a doorway to discovery rather than a sign of failure. Astronomers knew that by choosing an empty patch, giving Hubble weeks of exposure, and carefully calibrating every aspect of the observation, they could push the limits of what could be seen and potentially glimpse galaxies forming at the edge of time itself. The selection of this new patch followed the same philosophy, but was informed by more than a decade of experience. Advanced simulations, combined with previous survey data, allowed astronomers to identify regions where the probability of foreground contamination was minimal. They avoided bright stars, dense clusters, and regions affected by zodiacal light. They factored in the telescope's sensitivity, the filters available, and the exposure times necessary to reach the faintest signals. The result was a field that appeared statistically empty, almost a void, yet promised the greatest return in the deepest possible observations. Approval for the long exposure times was not granted lightly. Observing Hubble for days in a single position is a significant commitment, potentially preventing other astronomers from using the telescope. The case had to be justified scientifically. Astronomers argued that observing a region of apparent emptiness allowed them to maximize the telescope's unique capabilities. The patch offered the opportunity to detect galaxies at extreme distances, to measure their colors and structures, and to study the formation of stars and galaxies in the first billion years of cosmic history. Long exposures would reveal objects too faint for any other telescope, providing insights into the early universe that could not be obtained by surveying brighter, more cluttered fields. The science case was clear. Targeting nothing could illuminate everything. And yet, despite all the careful planning and preparation, the expectation was modest. Astronomers anticipated sparse background galaxies, a gradual rise in the noise floor, and a few faint sources scattered across the field. There was no reason to predict the statistical anomalies that would later astonish the scientific community. According to every model and previous survey, the patch should have been largely empty, a dark canvas punctuated by only a few faint points of light. The goal was to measure what was expected, to extend the limits of detection, and to provide a reference for future observations. The instruments themselves were essential to making this vision a reality. Hubble's Wide Field Camera, the advanced camera for surveys, and later the Wide Field Camera 3, allowed astronomers to capture light across visible and near-infrared wavelengths simultaneously. This capability ensured that even faint, red-shifted galaxies could be detected, their light stretched by billions of years of cosmic expansion into the near-infrared. The combination of optical and infrared observations provided a full picture of the distant universe, revealing galaxies invisible in visible light alone, and confirming the faintest detections as real rather than noise. In essence, aiming Hubble at this patch was a carefully orchestrated experiment. It was a calculated risk, grounded in decades of experience with deep field observations. The patch itself was selected for its statistical emptiness, minimizing interference and maximizing the ability to detect the faintest sources. Long exposure times were justified by the potential scientific payoff, the detection of galaxies at extreme distances, providing a window into the earlier stages of cosmic history. Every element, from the field's location to the instruments chosen, to the filters applied and the exposure time allocated, was optimized to turn apparent nothingness into a detailed, observable universe. When Hubble finally began its observations, the telescope entered the patch and started to collect photons that had traveled for over 13 billion years. For the first few hours, the field appeared as expected, dark, empty, with only a few faint sources emerging from the background. Every frame was carefully checked, every exposure stacked and calibrated, ensuring that each photon was properly accounted for. The background remained low, the noise gradual, and the field confirmed as statistically barren. Yet hidden within the faintest glimmers, at the limit of detectability, lay the seeds of the extraordinary discoveries that would later emerge. Once Hubble was pointed, once the long exposures began, the telescope became an eye in the void, staring into a corner of the universe that had, until that moment, been almost entirely invisible. For hours, days, and weeks, its instruments collected faint photons, one by one, tracing a journey that had begun more than 13 billion years ago. These photons had travelled through the expanding universe, past countless cosmic structures, and survived the gravitational tug of countless galaxies, only to arrive at Hubble's detectors, silent messengers from the deep past. At first, the patch lived up to expectations. The images were nearly black, a field of optical darkness with only the faintest hints of light breaking through. These faint sources were consistent with what astronomers had predicted: a sparse population of distant galaxies, small, faint, and scattered randomly. Noise from the detector, the inevitable background of cosmic light and faint residual zodiacal light, formed the only other signals in the frame. This was precisely the outcome the scientists had planned for: a test of the telescope's sensitivity and a way to calibrate expectations. But as exposures continued and the images were stacked, subtle structures began to appear. Tiny smudges of light that had been invisible in single exposures became detectable. These smudges were faint galaxies, some with a small, concentrated core of light, others elongated or clumpy, hinting at the beginnings of structure. Even at these extreme distances, galaxies were forming stars, producing radiation that had travelled for billions of years. Each photon from these smudges was carefully verified, compared across multiple filters, and cross-checked against other frames to ensure it was real and not a random artifact or cosmic ray. The first surprises came from the numbers. In a patch of sky that was expected to contain only a handful of galaxies, there were dozens, and soon hundreds. The density of these faint objects exceeded predictions, and their distribution was not entirely random. Some clustered slightly, suggesting the early formation of structure even in regions thought to be nearly empty. The field that had been chosen for its statistical emptiness was revealing a richness that models had not anticipated. Colour provided another clue. Hubble's optical and near-infrared filters allowed astronomers to estimate the distances of these galaxies. Light from extremely distant galaxies is stretched or redshifted into longer wavelengths by the expansion of the universe. By measuring the relative brightness in different filters, astronomers could determine which galaxies were nearby, which were in the middle distances, and which were at extreme distances formed only a few 100 million years after the Big Bang. The patch revealed galaxies spanning a range of redshifts, some within the expected range for deep field observations, others far beyond. Some were faint and red, almost invisible in the optical but glowing in infrared, confirming that Hubble's long exposures were reaching the earlier structures in the universe. The shapes of these faint galaxies were equally unexpected. Some were small and irregular, as cosmologists had predicted for young galaxies still forming stars and merging with neighbours. But others showed surprising structure, hints of spiral patterns, elongated cores, or clumpy regions suggestive of early star clusters. Even at these extreme distances, galaxies were not purely chaotic. The early universe, it seemed, was capable of producing structure far faster than expected, and this patch, chosen for its apparent emptiness, had revealed it in stunning clarity. Hubble's instruments were essential to uncovering these faint signals. The wide-field camera and the advanced camera for surveys captured optical light with incredible sensitivity, while the wide-field camera 3 extended Hubble's reach into the infrared. By combining these exposures, astronomers could detect galaxies that were invisible in one filter, but appeared clearly in another. The careful stacking of hundreds of exposures reduced noise to the absolute minimum, ensuring that even the faintest smudges of light were real. This combination of instrument precision, careful calibration, and long exposure time allowed Hubble to reveal galaxies that no other telescope could detect. As the images were analysed, astronomers realised that some galaxies were brighter than expected for their distance. Their luminosity implied a rapid rate of star formation, producing stars in large numbers far earlier than models had predicted. Others were extraordinarily faint, barely above the noise threshold, suggesting the existence of a hidden population of low luminosity galaxies that had previously escaped detection. Together, these findings suggested that the universe was more efficient at forming galaxies in its first billion years than any simulation had anticipated. The field also highlighted the difference between optical darkness, infrared emptiness, and radio silence. Many of the faint galaxies detected in the infrared were completely invisible in optical wavelengths, their light stretched into red and infrared by the expansion of the universe. In optical images, they were nearly absent, but in infrared, they glowed faintly, revealing their existence. Radio observations confirmed that the patch remained silent, with no detectable hydrogen clouds or other emissions. The combination of multi-wavelength observations allowed astronomers to understand that the patch's emptiness was only apparent, and that the early universe was teeming with faint galaxies, even in regions thought to be barren. One of the most surprising aspects was the apparent age of some of these galaxies. By analysing the light and comparing it to stellar population models, astronomers could estimate how long stars had been forming within them. Some galaxies appeared older than expected, suggesting that star formation had begun almost immediately after the first galaxies formed. These were not mere clouds of gas. They were structured, with hints of star clusters and regions of concentrated activity. The universe, it seemed, had begun building complex systems very quickly, and this patch, chosen for its emptiness, revealed that history in astonishing detail. Even the faintest galaxies told a story about the early universe. Their distribution hinted at the large-scale cosmic web, the network of filaments and voids that would later dominate the universe's structure. Some galaxies clustered along faint patterns, suggesting that the skeleton of the universe was already forming, even at extreme distances. The patch that had been chosen to be empty was revealing the beginnings of the cosmic architecture, the invisible threads that would later guide galaxy formation and clustering across billions of light years. Astronomers were careful to rule out every source of error. Could the faint smudges be detector noise? Could cosmic rays or instrumental artifacts have created false positives? Multiple teams reprocessed the images using different calibration pipelines, and independent analyses confirmed the presence of these faint galaxies. The faint population persisted, consistent across filters and exposures, confirming that the discoveries were real. The empty patch had become a crowded window into the early universe, and every photon told a story billions of years in the making. As Hubble's long exposures continued, the number of detectable galaxies increased. Each week of observation added more faint sources, pushing the limits of the telescope's sensitivity. The patch of sky that had been selected for statistical emptiness was gradually revealed as a treasure trove, containing hundreds of galaxies, some visible in optical light, others only in infrared. The diversity of these galaxies, both in shape and in brightness, challenged assumptions about the early universe and provided the first glimpse of how quickly structure could emerge from the primordial darkness. The discoveries were subtle but profound. A single image of the patch, when fully processed, contained more information than decades of ground-based surveys. Each faint galaxy was a record of the early universe, a snapshot of star formation, gas dynamics, and early cosmic structure. The patch that had been expected to show nothing statistically abnormal had instead revealed a universe more complex, more structured, and more abundant than astronomers had predicted. Every detail, from the faintest infrared glow to the elongated shape of a distant galaxy, suggested that the early universe was capable of producing order in ways that theory had not fully anticipated. In the quiet of space, photons continued to arrive, each one a tiny messenger from a distant galaxy, a record of events that had occurred billions of years ago. Hubble, floating above the Earth's atmosphere, captured these photons with precision, turning what had been a blank, statistically empty patch into a field filled with the faintest light the human eye, or even Earth-bound instruments, could imagine. This was the payoff for years of planning, careful selection, and long exposure times. A detailed view of galaxies forming at the edge of time, revealing a universe that was at once familiar in its physics and astonishing in its efficiency and complexity. The perfect window. Not all darkness is equal. The night sky may appear black to the naked eye, but astronomers know that every patch of sky carries its own character. Some regions are cluttered with stars from our galaxy, dense clouds of interstellar dust, or faint background glow that can obscure the faintest galaxies. Others are brighter due to sunlight scattered by tiny dust particles in the plane of the solar system, a phenomenon called zodiacal light. Selecting the right patch of sky for a deep field observation is not a matter of luck. It is a careful, deliberate choice that balances distance, clarity, and cleanliness to create the perfect window into the distant universe. The first and perhaps most subtle factor is zodiacal light. This is sunlight reflected and scattered by dust grains that orbit the Sun, lying primarily in the plane of the solar system. On Earth, zodiacal light is sometimes visible just after sunset or before sunrise, as a faint, diffuse glow stretching along the ecliptic. While it is almost invisible to casual observers, it is a persistent source of background light for telescopes in orbit. In the case of Hubble, even faint zodiacal light could overwhelm the weak signals of the most distant galaxies. Each photon from a galaxy billions of light-years away is precious, arriving after a journey across the cosmos. If the telescope's detectors are flooded with scattered light from nearby dust, those ancient photons may never be discerned. Selecting a patch with minimal zodiacal light was essential, a quiet corner of the solar system's glow where Hubble could see faint, distant galaxies without interference. Astronomers examined detailed maps of zodiacal light intensity across the sky, identifying regions where the glow was weakest. This became a key criterion, ensuring that the photons collected would truly belong to distant galaxies, rather than the dust surrounding our Sun. Minimal interference from the Milky Way was the second criterion, and it was just as critical. Our galaxy is a sprawling, luminous disk filled with stars, gas, and dust. While spectacular to behold, it is a dense forest of obstacles for astronomers seeking faint, distant galaxies. A telescope aimed at a crowded star field sees its detectors overwhelmed by bright points of light, making it difficult or impossible to detect objects that are billions of times fainter. Interstellar dust scatters and absorbs light, further obscuring the view. By selecting a patch at a high galactic latitude, far above the plane of the Milky Way, astronomers minimized the number of foreground stars and the amount of dust that could interfere with observations. The field became a quiet window, free from clutter, where every faint glimmer could be confidently identified as a distant galaxy rather than a nearby star. This is why deep field targets are rarely located near the plane of the Milky Way. The most productive windows into the early universe are found in the quiet outskirts, regions where our galaxy's interference is minimal. Instrument calibration was the third factor, an invisible but no less critical element of the selection process. Hubble's instruments are finely tuned machines capable of detecting single photons. However, they have limits. Detectors can be saturated by bright sources, miscalibrated by variable background light, or disrupted by thermal fluctuations in the telescope itself. Observing a field that is too bright, too crowded, or too variable risks contaminating the data and complicating analysis. Empty regions provide a stable baseline, allowing astronomers to separate faint signals from noise with confidence. Calibration frames, exposure stacking, and corrections for instrumental drift all work best when the background is predictable. A clean patch of sky ensures that what the telescope sees is real cosmic light, not artifacts introduced by the instruments themselves. These three criteria, low zodiacal light, minimal Milky Way interference, and instrument-friendly conditions, work together to create a near-perfect observation field. It was statistically quiet, meaning that almost nothing in the foreground would confuse the detectors. Photons from distant galaxies could travel unimpeded, their light reaching Hubble after billions of years. The telescope would not be forced to contend with bright stars, scattered sunlight, or variable backgrounds. In essence, the patch of sky was optimized to reveal the faintest objects in the universe, the earliest galaxies, and structures that had formed when the cosmos was still in its infancy. The choice of the patch was guided by more than maps and simulations. Hubble's previous deep field projects provided a blueprint. The original Hubble Deep Field in 1995 had shown that staring at a tiny, statistically empty patch for days could reveal hundreds of galaxies. By 2003, the Hubble Ultra Deep Field had pushed even further, combining optical and infrared observations to reveal galaxies that existed when the universe was less than 1 billion years old. Each success reinforced the importance of careful target selection. Empty regions were not chosen randomly. They were chosen because their emptiness allowed the telescope to reach further than ever before. Even within these empty regions, subtle differences mattered. The angle of observation relative to the Sun affected zodiacal light. The location relative to the galactic plane affected Milky Way interference, and the telescope's own thermal state influenced instrument sensitivity. The patch that would eventually reveal the most distant galaxies was selected after months of analysis, calculations, and simulations. Every factor was optimized. The field was small enough to allow long, stable exposures without introducing motion blur, yet large enough to contain hundreds of potential galaxies. The low background light ensured that faint sources could be detected with confidence, and the absence of foreground clutter made the data easier to analyze. Instrument calibration also determined the timing and filters used. Hubble's cameras are sensitive across a wide range of wavelengths, from ultraviolet to near-infrared. Selecting the right filters was critical to detect the faint, red-shifted light of the most distant galaxies. Long exposures in multiple filters allowed astronomers to not only detect these galaxies, but to measure their colors, estimate their distances, and study their properties. Each filter added another layer of information, and each required careful calibration to ensure that the light captured was accurate and not influenced by the telescope's own electronics or optics. The patch's combination of low zodiacal light, minimal Milky Way interference, and calibration-friendly conditions made it uniquely suited for deep field observation. It was a deliberate choice, not a gamble. Hubble would spend hundreds of hours accumulating photons from this region, stacking exposures, correcting for noise, and building the deepest image of the universe ever obtained. In doing so, it would reveal galaxies that were previously invisible, galaxies that formed when the universe was less than 1 billion years old, and structures that challenged every expectation about the early cosmos. Even before Hubble began observing, the patch represented a triumph of planning and strategy. Astronomers had identified a region where every photon could be traced to distant galaxies rather than local interference. They had calculated exposure times, filters, and calibration needs. They had minimized the effects of zodiacal light and galactic foreground. The patch of sky was a laboratory designed to test the limits of observation, a carefully chosen window into the earliest universe. When Hubble finally aimed its cameras at the patch, the preparation paid off immediately. For the first few hours, the field appeared dark, just as predicted. Gradually, as exposures accumulated and photons were stacked, faint smudges began to emerge, each one a distant galaxy, billions of light years away. The statistical emptiness of the patch made these discoveries possible, turning what was invisible into a detectable, measurable, and profoundly significant window on the early universe. The success of the observation depended entirely on the careful selection criteria. Low zodiacal light ensured that scattered sunlight did not drown out faint signals. Minimal Milky Way interference ensured that bright stars and dust did not obscure the view. Instrument calibration needs ensured that Hubble's cameras could operate at peak sensitivity without risk of saturation or noise contamination. Together, these factors transformed a patch of apparent nothingness into a field of galaxies, each a beacon from the dawn of cosmic history. This patch, chosen with scientific precision, illustrates a central principle of deep field astronomy. Sometimes the most important discoveries come not from looking at the brightest, closest objects, but from aiming carefully at emptiness, where the universe's earliest secrets lie hidden. The field's extreme quiet allowed Hubble to capture photons that had travelled across more than 13 billion years, revealing galaxies at the edge of the observable universe and providing insights into cosmic history that had been impossible just a decade earlier. Waiting for the faintest light. Time is a telescope's most powerful ally. In space, where photons from distant galaxies travel for billions of years, waiting is the only way to capture the faintest signals. Hubble's instruments are extraordinarily sensitive, capable of detecting single photons of light, but even they require time. Each photon from a distant galaxy is precious, rare, and often indistinguishable from the background noise unless enough light is collected. The approval for long exposure time was not a trivial decision. Orbiting the Earth is a telescope in high demand, with countless astronomers and institutions vying for each hour of observation. Every second of Hubble's gaze spent in one patch is a second not spent elsewhere. Convincing the scheduling committees to dedicate days, even weeks, to a single field required a clear scientific justification, precise predictions, and careful planning. The rationale was rooted in the physics of light and the nature of distant galaxies. Galaxies that formed in the first billion years of the universe are extraordinarily faint. They are small, dim, and their light has been stretched or redshifted by cosmic expansion into the infrared. In visible light, many of these galaxies are effectively invisible. Only through prolonged observation can enough photons accumulate to reveal their presence. The longer Hubble stares, the more photons it collects, and the fainter the galaxies it can detect. Short exposures would only capture the brightest, nearest galaxies, leaving the early universe almost entirely hidden. To see back to the cosmic dawn, astronomers needed hours, days, and even weeks of continuous observation, allowing the faintest whispers of light to emerge above the statistical noise inherent in any detector. Astronomers had a clear expectation for what the field would yield. Based on prior surveys and deep field experience, they predicted sparse background galaxies scattered across the patch. The field was chosen precisely because it lacked bright foreground stars or dense galactic interference. What Hubble would see, they assumed, was the faint signature of galaxies, each appearing as a small smudge or faint point of light, gradually rising above the background as exposures accumulated. They expected the gradual noise floor, an inevitable hum from the telescope's electronics, cosmic rays, and diffuse light to dominate at first, obscuring these faint sources until sufficient photons were collected. The field was expected to be quiet, nearly featureless, with nothing statistically abnormal or unusual. This expectation guided the planning of exposure times, the selection of filters, and the overall strategy of observation. The longer Hubble stares, the more photons it collects, and the fainter the galaxies it can detect. Short exposures would only capture the brightest, nearest galaxies, leaving the early universe almost entirely hidden. To see back to the cosmic dawn, astronomers needed hours, days, and even weeks of continuous observation, allowing the faintest whispers of light to emerge above the statistical noise inherent in any detector. Astronomers had a clear expectation for what the field would yield. Based on prior surveys and deep field experience, they predicted sparse background galaxies scattered across the patch. The field was chosen precisely because it lacked bright foreground stars or dense galactic interference. What Hubble would see, they assumed, was the faint signature of galaxies, each appearing as a small smudge or faint point of light, gradually rising above the background as exposures accumulated. They expected the gradual noise floor, an inevitable hum from the telescope's electronics, cosmic rays, and diffuse light to dominate at first, obscuring these faint sources until sufficient photons were collected. The field was expected to be quiet, nearly featureless, with nothing statistically abnormal or unusual. This expectation guided the planning of exposure times, the selection of filters, and the overall strategy of observation. Long exposure times were approved not as an experiment in the unknown, but as a scientifically calculated method to push observational limits. Astronomers could justify dedicating Hubble to the field for dozens of hours because the payoff was measurable. Each additional hour would increase sensitivity, allowing the telescope to detect galaxies previously beyond reach. The exposure strategy was precise. Repeated observations in multiple filters allowed astronomers to separate real faint galaxies from noise, cosmic rays, and instrumental artifacts. Stacking hundreds of exposures, each carefully calibrated, would gradually reveal a faint population of background galaxies, building a deep, high-fidelity image of the distant universe. The expectations were grounded in statistical modelling. Cosmologists had mapped galaxy distributions, analysed luminosity functions, and predicted the number density of faint galaxies at extreme distances. These models suggested that the field should be nearly empty, with only a small number of faint galaxies per square arc minute. Noise would dominate the initial frames, but over time the galaxies would emerge. The scientists anticipated smooth behaviour, a gradual accumulation of detectable sources with no surprises. They did not expect to find an overabundance of galaxies or anomalously bright objects. Their goal was to test the limits of Hubble's sensitivity, to confirm predictions, and to provide a baseline for future cosmological studies. The technical considerations were just as critical. Hubble's instruments operate with remarkable precision, but faint signals can be easily confused with detector noise. Long exposures reduce random fluctuations, allowing astronomers to identify real sources with confidence. They planned for continuous observation blocks, minimizing interruptions that could introduce artifacts or inconsistencies. Filters were chosen to capture both optical and near-infrared light, maximizing the ability to detect redshifted galaxies from the earliest epochs. Calibration procedures ensured that each photon counted and that background noise could be accurately subtracted. In essence, the telescope was trained to wait patiently, to accumulate light until the faintest galaxies revealed themselves. The scientists also considered cosmic and instrumental factors that could influence the results. Zodiacal light, though minimized by the choice of field, still added a subtle background that had to be accounted for. Thermal fluctuations in the telescope could introduce slight variations in sensitivity. Cosmic rays striking the detectors could create false signals. Every element had to be anticipated, every risk mitigated, to ensure that long exposures would produce reliable data. Approving the observation time was a statement of confidence. Confidence in Hubble's stability, its instruments, and the ability of astronomers to extract meaningful information from the faintest light in the universe. From the very first hours, the field appeared almost exactly as predicted. Initial exposures showed a smooth noise floor, faint hums of electronic and cosmic background, and only the occasional hint of a faint source. The field lived up to its statistical emptiness, a nearly perfect blank canvas. Yet as exposures accumulated, subtle smudges began to emerge. tiny, faint galaxies appeared, almost imperceptible against the background, each photon confirming a distant object billions of light-years away. The gradual revelation of these sources validated the planning and the exposure strategy. What had been invisible became detectable, each additional hour of observation increasing clarity and depth. Astronomers watched with anticipation. The long exposures were necessary because the faintest galaxies are not immediately visible. They require patience and accumulation. A single hour would reveal nothing new. A single night would produce only partial results. But over weeks of observation, photons from distant galaxies gradually rose above the noise, their faint light building a detailed picture of a region previously assumed to be nearly empty. Each faint smudge added to the story of cosmic history, revealing galaxies that had formed when the universe was still young. Structures that could inform theories of galaxy formation, star formation, and the distribution of matter in the early cosmos. The expectation of statistical normality guided interpretation. Astronomers knew that the field should contain only a sparse number of galaxies, and that these galaxies should be faint and irregular. They did not anticipate anomalies, overdensities, or objects that defied cosmological models. This expectation was crucial because it provided a benchmark. Any deviation from the predicted sparse distribution would signal something extraordinary. In other words, the field was a controlled experiment. Long exposures would reveal what was expected, establishing a baseline for understanding the distant universe. Only then could unexpected discoveries be recognized as significant. The approval of long exposure time was thus both practical and visionary. It was practical in the sense that longer exposures were necessary to detect faint galaxies and confirm models. It was visionary because the observations could extend humanity's view to the earliest epochs of the universe. Hubble's stability and sensitivity, combined with meticulous planning, allowed astronomers to extract meaningful signals from what initially appeared to be empty space. The long exposures were an investment in patience, confidence that the faintest light would eventually emerge from darkness, and a calculated risk that the universe would reveal its history if given time. How Hubble actually sees darkness. Darkness in space is not truly empty. Even the void between stars and galaxies contains faint signals, cosmic background light, and subtle interference from instruments themselves. For the human eye, these signals are invisible. For Hubble, they are everything. Seeing darkness is not about looking at blackness. It is about detecting the faintest photons, measuring them accurately, and distinguishing them from every possible source of noise. Hubble does not simply capture an image. It counts particles of light, builds layers of information, and turns the near invisible into observable structure. Hubble relies on its suite of cameras, each designed for precision and sensitivity. The Wide Field and Planetary Camera 2, known as WFPC-2, was the workhorse for the early deep field studies. Its sensors were capable of detecting extremely faint light while maintaining high spatial resolution. Later, the Advanced Camera for Surveys, ACS, enhanced Hubble's ability to detect faint galaxies in optical wavelengths, with improved quantum efficiency and lower readout noise. The Wide Field Camera 3, WFC-3, extended Hubble's reach into the near-infrared, a critical range for observing high redshift galaxies whose light has been stretched by billions of years of cosmic expansion. Each instrument was calibrated for maximum sensitivity, tuned to detect individual photons without being overwhelmed by brighter sources or internal noise. The process begins with exposure. Hubble stares at a patch of sky for hours, sometimes days, allowing photons to accumulate on the detectors. Each photon is a messenger, carrying information about a galaxy, a star, or intergalactic gas. But faint photons are rare. The farther the source, the fewer photons reach the telescope per unit time. Capturing enough light to see these distant objects requires long exposures, repeated over multiple sessions. Each image, or exposure, contains a combination of signal, the light from real cosmic objects, and noise, the random fluctuations introduced by the telescope, the detectors, and the space environment. To extract meaningful information, astronomers use a technique called exposure stacking. Each exposure is carefully aligned, calibrated, and combined with previous images. Over hundreds of hours, faint photons add up, while random noise averages out. Signal increases proportionally with time, but noise increases more slowly, improving the signal-to-noise ratio. This is why darkness, paradoxically, can increase sensitivity. The emptier the field, the fewer interfering sources, the more effectively Hubble can isolate faint photons. Statistical methods allow astronomers to distinguish real sources from spurious fluctuations, revealing galaxies that are billions of times fainter than anything visible with ground-based telescopes. Counting photons is a precise, delicate process. Each detector pixel records incoming photons as a discrete event. Electronics measure the energy deposited by each photon, registering it as a count. Repeated over time, this produces an image where brightness corresponds to the number of photons collected. Even a single photon matters. For the most distant galaxies, the cumulative number of photons collected may only be a few per hour per pixel. This is why Hubble's instruments are cooled, shielded, and finely tuned. Any additional signal from heat, electronics, or cosmic interference could overwhelm the subtle light from distant galaxies. Noise is inevitable, even in space. Cosmic rays, high-energy particles from outside the solar system, strike the detectors constantly. Each cosmic ray produces a signal that can mimic or obscure a photon from a distant galaxy. Detector dark current, the small amount of charge generated in a sensor even without light, adds another background signal. Thermal noise arising from minute temperature variations in the instruments introduces further uncertainty. To manage these, Hubble performs calibration exposures before and after observing the target. These calibrations measure the intrinsic response of the detector, the rate of dark current, and the pattern of thermal noise. By subtracting these known contributions from the science exposures, astronomers isolate true photons from distant galaxies. Even the smallest detail matters. Detector imperfections can create hot pixels, tiny points of artificially high signal, or readout errors that introduce subtle streaks. Multiple exposures allow astronomers to identify and reject these artifacts. Cosmic rays, which strike randomly, appear in only one exposure. Stacking multiple images ensures these spurious signals do not contaminate the final result. Every pixel is treated as a data point, every photon as evidence, and every exposure as a building block toward a final, high-fidelity image of the distant universe. The process of seeing darkness also depends on wavelength. OCS and WFPC2 operate primarily in the optical range, where distant galaxies are faint but still detectable. WFC3 extends into the near-infrared, crucial for observing galaxies whose light has shifted to longer wavelengths due to the expansion of the universe. Infrared light passes through interstellar dust more easily than visible light, making these instruments ideal for peering into regions that would otherwise be obscured. Each instrument requires its own calibration, accounting for detector response, optical distortions, and filter transmission. The combination of optical and infrared observations provides a multi-layered view of the universe, revealing galaxies at different stages of formation and at different distances. As exposures accumulate, the image evolves. Initially, the field appears nearly black, punctuated by random noise and occasional cosmic ray hits. After hours of integration, faint smudges emerge. Over days, these smudges sharpen, revealing the shapes, colours and distributions of distant galaxies. Exposure stacking, calibration and noise subtraction work together to transform near-invisible light into detailed maps of the universe. Each detected photon contributes to an understanding of the early cosmos, providing information about galaxy formation, star formation rates, and the large-scale structure of the universe. Even darkness is a canvas of information. The absence of bright sources allows Hubble to reach unprecedented sensitivity. Every faint photon that reaches the detector is preserved, analysed, and interpreted. The process is meticulous. Calibration frames remove instrumental artifacts, exposure stacking boosts the signal of real sources, and careful analysis distinguishes galaxies from noise. In this way, Hubble converts emptiness into discovery, turning statistical nothingness into detailed images of the distant universe. The combination of WFPC2, ACS, and WFC3 over decades demonstrates the evolution of Hubble's ability to see darkness. Each new camera brought improvements in sensitivity, stability, and wavelength coverage. WFPC2 laid the foundation for the first deep-field images. RCS allowed astronomers to detect galaxies at fainter magnitudes and map their distribution more accurately. WFC3 extended Hubble's vision into the infrared, capturing light from the earliest galaxies in the universe. Across all instruments, the principles remained the same: long exposure, careful calibration, photon counting, and rigorous noise management. Even the quietest patch of sky contains subtle signals that can overwhelm detection if not properly accounted for. Zodiacal light, though faint in these regions, introduces diffuse background that must be subtracted. Faint stars from the Milky Way may appear as tiny points, requiring careful masking to avoid contamination. Every exposure is meticulously reviewed, with cosmic rays and hot pixels identified and removed. The final image is a composite of hundreds of hours of data, a representation of the universe as it appears in its faintest, most distant form. Hubble sees darkness not as empty space, but as a field of information. Each photon represents light that has travelled billions of years, a record of star formation, galaxy evolution, and cosmic structure. By carefully stacking exposures, calibrating instruments, and accounting for noise, astronomers can reveal objects that are billions of times fainter than anything visible to the human eye. Even statistical nothingness becomes meaningful, a measure of the faintest galaxies and the limits of observable space. In practice, seeing darkness requires patience, precision, and an understanding of every source of noise. Cosmic rays, detector dark current, and thermal fluctuations are not obstacles to be ignored. They are measurable phenomena that must be accounted for. Calibration frames taken before, during, and after observation provide the baseline. Exposure stacking builds the signal gradually. Noise subtraction isolates real photons. Each step is designed to ensure that when a faint smudge of light appears, it is real, traceable, and scientifically valid. The result is extraordinary. What appears as empty space to the naked eye becomes a rich landscape of distant galaxies. Hubble converts what seems to be darkness into a census of the faintest cosmic objects, mapping the universe at scales and distances unimaginable before its instruments. Each image tells a story, not of the void, but of light that has travelled billions of years, revealing the earliest galaxies, their distribution, and the structure of the cosmos. The first sign something was wrong. Hubble had been staring at the patch of sky for days. Hours stretched into nights, nights into weeks. Each exposure added faint smudges, photons that had travelled billions of years, slowly building the image of a distant universe. At first, everything behaved exactly as expected. Sparse galaxies appeared in the distance, faint and isolated, each one consistent with models. Noise levels were steady, random, unremarkable. Everything was normal. Until, slowly, it wasn't. The first hint came in the photon counts. Detectors that had measured nearly nothing in the background suddenly registered slightly more light than predicted. At first, it was subtle, a handful of extra photons in isolated pixels. But as exposures accumulated, the pattern became impossible to ignore. The faint signals weren't random. They appeared repeatedly in the same positions, across multiple exposures, in a way that statistical noise could not explain. Each photon added weight to the idea that something unusual was lurking in the darkness. These were not bright objects, not stars shining in the foreground, not artifacts caused by cosmic rays. They were faint, diffuse, and oddly structured. When the data from different filters were compared, a strange consistency emerged. In optical wavelengths, tiny smudges appeared where no galaxies were expected. In the near-infrared, the same regions lit up, sometimes brighter than expected, for objects that should be faint and redshifted. The light was distributed in a way that defied the models astronomers had built over decades. Random noise, after all, does not repeat across filters. Random noise does not produce faint, extended structures. Random noise does not produce the subtle but coherent colours that these smudges carried. The patterns were the first sign that the universe might be trying to tell something entirely unexpected. The team stared at the early images with cautious disbelief. Could it be an error in the detector? Hubble's cameras were extraordinarily stable, but no instrument is perfect. Could this be a cosmic ray, a hot pixel, or a momentary electronic glitch? The team ran every known test. Calibration frames, dark exposures, and flat fields were checked again and again. Each check confirmed the detectors were working exactly as they should. There was nothing in the hardware to explain the repeated, faint, structured light. Processing artifacts were another possibility. Images taken by Hubble undergo extensive processing. Exposures are aligned, stacked, corrected for distortions, and filtered to remove cosmic rays and other noise. Could the stacking process have introduced false smudges? To test this, raw images were inspected frame by frame before any stacking or corrections. The faint structures were still there. Every frame confirmed their presence. The light was real, not a mistake of human analysis. Independent verification was essential. Separate teams, both inside and outside the original collaboration, analysed the data. They used different software, alternative stacking algorithms, and independent calibration pipelines. Every check produced the same result. The faint structures persisted. Their positions, shapes, and colours were consistent across teams. Statistical confidence thresholds were exceeded. The probability that these signals were random noise or errors was vanishingly small. In the language of science, this was beyond a mere anomaly. It was a genuine, measurable deviation from expectation. Signal-to-noise ratios, the measure of how strongly a real signal stands out from background noise, confirmed the oddity. In multiple exposures and across multiple wavelengths, the faint sources had higher SNR than any random fluctuation should allow. Photons that should have been scattered randomly across the field appeared clustered. They were structured. They carried information. They were repeating, coherent, measurable, and impossible to dismiss as chance. Colour anomalies added another layer of mystery. Using Hubble's filters, astronomers could measure the relative brightness of objects in different parts of the spectrum. Galaxies at known distances have predictable colours depending on their redshift. But these faint smudges did not match predictions. In some cases, objects appeared slightly bluer than models suggested, in others, slightly redder. They showed colour gradients where none should exist. Across optical and infrared filters, the patterns were consistent, yet anomalous. Every wavelength confirmed the same unexpected behaviour. Every photon aligned with something that models could not yet explain. Even the faint structures themselves were peculiar. Rather than appearing as round, uniform blobs typical of distant, faint galaxies, they showed subtle asymmetry, wisps, and faint extensions. These were not artifacts created by the telescope optics. The structures appeared in multiple independent instruments, WF, P, C2, ACS, and WF-C3. They were repeatable, consistent across time, and observed in exposures separated by days and weeks. The longer the telescope stared, the more detail emerged. The field was no longer just sparse background galaxies. It was something else entirely. The exact wavelengths involved were critical to the growing suspicion. In optical bands, the smudges were faint but visible. In near-infrared bands, where the light of ancient galaxies would have redshifted, some objects appeared brighter than expected. The combination of optical faintness and infrared brightness suggested extreme distances, possibly galaxies forming when the universe was still in its infancy. The photons were arriving as expected in timing and energy, but their distribution, colours and structures violated prior statistical models. This was not just a measurement error, it was a cosmic signal. Teams ran statistical analyses on the photon counts. Random fields should produce random distributions of faint signals, and faint galaxies should be scattered predictably based on known luminosity functions. Yet in this field, photons clustered in non-random ways. Extended faint structures appeared where none should exist. Signal-to-noise ratios exceeded confidence thresholds, and repeated observations confirmed the pattern. The probability of this being a fluke was astronomically small. Something real, something previously unobserved, was emerging from the void. Every precaution, every cross-check confirmed the truth. Instrument error was ruled out. Background noise could not reproduce the repeated smudges. Processing artifacts were eliminated by analysing raw frames independently. Multiple teams verified results. Every measure pointed to the same conclusion. The darkness Hubble had aimed at was not empty. It was filled with faint light in ways no one had predicted. The escalation was subtle at first. It began with extra photons, small deviations from statistical expectation. Then the structures appeared, diffuse and coherent. Then the colours revealed themselves, anomalies in filters that should have been predictable. And finally, the statistical significance became undeniable. The team realised that something truly unexpected was in this dark patch of sky, something that would force a reconsideration of what empty really meant. The first sign something was wrong was not dramatic, not like a flash of light or a sudden discovery. It was quiet, persistent, and cumulative. Hubble's instruments, perfectly calibrated and optimized, began revealing faint structures that should not have been there. The photons themselves whispered a story that had been travelling across the universe for billions of years, one that contradicted everything astronomers had expected in a field that had been carefully chosen for its emptiness. The patch, selected for low zodiacal light, minimal Milky Way interference, and calibration-friendly conditions, had served its purpose perfectly. It was empty, except that it wasn't. The darkness had revealed itself as something far more complex, far more detailed, and far more anomalous than anyone could have predicted. Each exposure added certainty, each filter confirmed the anomaly, and each independent check strengthened the case. Even in the quiet of space, light spoke. Photons collected over hours and days carried information about distant galaxies, about cosmic history, and about structures that models had never predicted. The first sign that something was wrong was subtle, almost invisible. But it was there. A faint excess of photons, non-random distributions, strange colour signatures and extended structures all pointed to a truth that the team could no longer ignore. Hubble's deep stare into darkness had gone beyond expectation. sparse background galaxies appeared as predicted, but the anomalies, the faint, structured, repeated signals, emerged against every expectation. The patch of sky that should have been statistically empty had become a scene of cosmic mystery. Every photon counted, every filter confirmed, and every team verified. The universe had revealed something impossible, hidden in the darkness, waiting for someone patient enough, careful enough, and observant enough to notice. The galaxies that were too many. When the images were finally processed, the team froze. The faint smudges Hubble had collected over countless hours had grown into something far larger than anyone expected. There were galaxies everywhere, small pinpricks of light, tiny spirals and blobs, stretching across the carefully chosen patch of sky. The number was staggering, in a region that had been selected for statistical emptiness, for clarity, for near-perfect isolation from foreground stars and dust. The galaxies were not sparse. They were crowded. They were abundant. They were too many. Cosmologists had models for exactly this kind of deep field observation. Using the standard lambda cold dark matter model, lambda CDM, they could predict how many galaxies should appear at any given redshift, any given patch of the sky. Lambda CDM is the backbone of modern cosmology, the theory that explains how dark energy and dark matter drive the growth of structure in the universe. According to it, at extreme distances, galaxies seen as they existed just a few 100 million years after the Big Bang, the number of galaxies per square arc-minute should be low. Only the most massive and luminous objects should be detectable. The early universe should be sparse. The patch of sky that Hubble had surveyed should have been quiet. Instead, it teemed with galaxies. The counts were immediately obvious. Previous deep fields, like the Hubble Ultra-Deep Field, had revealed dozens, maybe a few hundred galaxies per square arc-minute, consistent with lambda CDM predictions. But in this region, the numbers exceeded expectations dramatically. Hundreds, sometimes over 1,000 faint galaxies appeared in the same area. It was as if the universe had packed more structure into this patch than simulations allowed. Astronomers compared the observed counts with thousands of cosmological simulations. Every model predicted far fewer galaxies at these redshifts. The discrepancy was not slight. It was glaring. Redshift estimates confirmed the impossibility. Using photometric techniques across multiple filters, the team measured the stretching of light from these galaxies. Many appeared at redshifts corresponding to less than 1 billion years after the Big Bang. In other words, these galaxies existed at a time when lambda CDM predicted the universe should still be largely diffuse. Gravity had not yet had enough time to pull together this many galaxies into detectable concentrations. The abundance of objects suggested that star formation and structure formation had proceeded much faster than the most successful models could account for. The luminosity function added another layer of mystery. Normally, distant galaxies obey a predictable distribution of brightness, with many faint galaxies and fewer bright ones. These galaxies did not fit. Not only were there more galaxies than expected, but some were surprisingly bright given their redshift. In cosmological simulations, galaxies of this brightness should have been extremely rare at such early times. Observers were seeing objects that defied the standard models both in number and in luminosity. Galaxies that seemed to have formed stars at a furious pace, far faster than theory allowed. The implications for early structure formation were profound. Galaxies do not emerge fully formed. They grow through the collapse of gas, star formation, and mergers with smaller structures. To see this, many galaxies in this volume, at this epoch, suggest that the early universe was far more efficient at creating structure than models had anticipated. Dark matter halos, the invisible scaffolding around which galaxies form, would need to have collapsed and coalesced faster than expected. Gas cooling, star formation, feedback processes, all the physics that regulate galaxy growth would have had to operate differently or more efficiently than our current understanding allows. Even more striking was the clustering. These galaxies were not randomly distributed. Many appeared in faint groupings, hints of protoclusters, which should not exist at this early epoch, according to lambda-c predictions. The presence of structure at these scales so early in cosmic history challenges the timing of hierarchical formation, the backbone of the standard cosmological model. Galaxies of this density and clustering should only appear later, hundreds of millions of years afterward. Yet here they were, already forming a web of connections in the darkness. Observers measured the counts per square arc minute with painstaking precision. In the optical and near-infrared bands, each detector pixel revealed multiple galaxies. When the data were combined and statistical corrections applied, the density of galaxies exceeded predictions by factors of 3, 4, sometimes even 10 in certain regions. This was not a small discrepancy. It was a fundamental challenge. Every galaxy counted, every photon confirmed, every exposure verified. The data was solid. Hubble's instruments were functioning perfectly. Independent teams verified the results. There was no error, no artifact, no fluke. Color information deepened the mystery. Many of the galaxies showed unusual spectral energy distributions. Some were bluer than expected, suggesting ongoing intense star formation. Others were redder, indicating the presence of dust and already mature stellar populations. The diversity of colors, combined with the sheer number of galaxies, was astonishing. It implied that star formation in the early universe was not only rapid, but also widespread and varied. The universe, at less than 1 billion years old, was already producing a rich tapestry of galactic environments. This abundance of galaxies also contradicted the predicted cosmic variance. Even in a statistically typical patch of sky, fluctuations in galaxy counts are expected due to randomness in large-scale structure. Yet the observed density was far outside any plausible variance. Every simulation run with lambda-c parameters failed to reproduce this level of clustering and abundance. The early universe, at least in this patch, was behaving in a way that no model had predicted. The team spent weeks double-checking every calculation. Photometric redshifts were cross-verified with multiple filters, exposures were reprocessed, and instrument calibrations were repeated. Every check reinforced the same result. The galaxies were real, abundant, and impossibly early. Signal-to-noise ratios across exposures were high, confirming that these were not faint noise spikes, but real photons from distant objects. Statistical confidence thresholds were exceeded. There was no room for doubt. As the analysis deepened, the scale of the problem became clear. The number of galaxies implied a universe that had formed structure faster than the lambda-c framework allows. Star formation rates, dark matter halo formation, and gas cooling times all seemed inconsistent with the observations. Models that had accurately reproduced galaxy counts in every other deep field failed completely here. The impossible nature of the objects became undeniable. These were galaxies that should not exist, at least not in the numbers, densities, and brightness observed. Even the sheer visual impression was striking. Looking at the stacked images, astronomers could see hundreds of faint galaxies in a patch of sky smaller than the angular size of a full moon. Each tiny smudge was a distant galaxy, each photon a record of star formation billions of years ago. The density was almost claustrophobic compared to the predictions. In some regions, the galaxies seemed to form faint chains or clumps, protostructures that hinted at complexity forming at an impossible speed. The discovery sparked immediate discussions. Could early star formation and galaxy assembly have been far more efficient than previously thought? Were there unknown physical processes accelerating structure formation in the first billion years? Or was the lambda-c framework incomplete, missing critical elements in the early universe? These questions could not be answered immediately, but the data itself was undeniable. Hubble had revealed a universe that was far richer, more crowded, and more complex than any simulation had predicted. Objects that were too old and too structured. As astronomers examined the light from these distant galaxies in detail, they noticed something unexpected. It wasn't just the number of galaxies that defied predictions. It was their age, their composition, and the subtle patterns hidden within their faint glows. The stars inside these galaxies were far older than anyone had expected. They were already evolved, already formed, and already showing signs of a history that should not have existed at such an early epoch. Astronomers analyze the age of stars by looking at their light in multiple wavelengths. Each star emits a spectrum of colors, and this spectrum carries a fingerprint of its age and chemical composition. Young stars shine brightly in blue light, their surface temperatures hot, and their cores still burning hydrogen at a furious pace. Older stars shift toward redder light, cooler in temperature, with elements heavier than hydrogen, what astronomers call metallicity, building up in their atmospheres. By comparing the observed colors of distant galaxies to models of stellar evolution, scientists can estimate the average age of the stars within them. In these early galaxies, the analysis produced a paradox. Many stars were far more evolved than the universe's timeline should allow. At redshifts corresponding to less than 1 billion years after the Big Bang, the universe itself was still extremely young. Yet the stellar populations indicated ages of hundreds of millions of years. This suggested that stars had begun forming almost immediately after the universe became transparent to light, accelerating faster than any prior model predicted. Stars in some galaxies had already burned through significant portions of their hydrogen. Some had produced heavier elements, and some galaxies showed signs of repeated star formation cycles. According to standard lambda CDM models, this shouldn't have been possible. The timeline simply didn't allow for it. Metallicity offered another clue. Stars forge heavier elements through nuclear fusion, releasing them into their surrounding environment via supernova explosions. By measuring the relative abundance of elements like oxygen, carbon, and iron in these galaxies, astronomers can trace the star formation history. Many of the galaxies in this deep field exhibited metallicities higher than expected for their age. The presence of heavy elements so early implied a generation of stars had already lived and died before these galaxies were observed, compressing star formation into a surprisingly short window. The early universe was producing complex chemistry at a speed that no simulation had predicted. Age dating stars at such extreme distances is a delicate process. Light has travelled billions of years to reach Hubble's detectors, stretching into the infrared due to cosmic expansion. By measuring the brightness across multiple filters, astronomers reconstruct the galaxy's spectra and compare them with models of stellar evolution. Signal-to-noise ratios in these faint objects are critical. Even a few miscounted photons can skew age estimates, yet in this case, repeated observations confirm the results. Different instruments, different teams, and different stacking techniques all returned the same startling ages. The stars were genuinely older than expected. As the team delved deeper, another puzzle emerged. Some of the faintest galaxies were not the amorphous blurry object simulations had predicted for such an early epoch. Instead, they showed structure. Disk-like shapes, clumps of concentrated stars, and hints of spiral arms. In the standard picture, early galaxies should be chaotic and irregular, still assembling from smaller clumps of matter. Gravity needs time to shape galaxies into disks and to form internal patterns. Yet here, in a universe barely 1 billion years old, Hubble revealed order amid the chaos. The morphological complexity was subtle, but undeniable. Advanced algorithms analyzing the light distribution within these galaxies detected faint central concentrations, suggesting the beginnings of a bulge and asymmetric clumps that hinted at localized star formation regions. Some galaxies displayed elongated shapes, hinting at disk formation, while others showed faint spiral-like arms. These patterns were not perfect spirals or fully formed disks, but they were structured, coherent, and highly organized for their age. For the faintest galaxies to exhibit this level of internal structure was entirely unexpected. Simulations of the early universe had consistently shown a different picture. Galaxies at redshifts corresponding to less than 1 billion years after the Big Bang should appear as irregular, diffuse blobs. Matter should be loosely clumped, gas clouds unshaped, and star formation scattered randomly. Disk formation and organized morphology were processes that were expected to occur much later, over hundreds of millions of years of hierarchical assembly. Yet Hubble's deep field images showed that these faint galaxies were already assembling in an orderly way. The combination of faintness and structure was particularly challenging. Faint galaxies are difficult to observe, and structure within them is often smoothed out by limited resolution and signal-to-noise constraints. Yet the exposure times in this field were long enough to resolve these tiny details. The disk-like features, clumpy star-forming regions, and central concentrations appeared repeatedly across exposures and filters, confirming that they were real, not artifacts of processing. Multiple instruments and independent teams verified the structural analysis, leaving little doubt. This suggested that galaxy assembly was accelerating at an unexpected rate. Star formation, feedback processes, and gravitational collapse must have operated more efficiently than current models predict. Dark matter halos must have formed, merged, and concentrated faster, pulling gas into potential wells capable of producing organized galaxies far earlier than theorists imagined. The faint galaxies were revealing that cosmic evolution had a head start, a speed that no simulation had accounted for. The implications were enormous. Galaxies that were too old and too structured challenged both the timeline and the mechanisms of early universe evolution. The early universe was not a slow, gradual assembly of stars and galaxies. Instead, it appeared dynamic, efficient, and surprisingly organized. Star formation had ignited quickly, metallicity built up rapidly, and galaxies developed internal structure far earlier than expected. These findings did not just tweak existing models, they demanded a fundamental rethinking of early cosmic history. The images themselves told a story that statistics alone could not. Tiny galaxies, barely resolved, glimmered with light that had travelled over 13 billion years. The faint disks, the clumpy star-forming regions, the colour variations across filters, all suggested that these galaxies had already lived a complex life. They were not newborn smudges of gas and stars. They were already old, already organised, and already defying the expected patterns of cosmic evolution. Every check reinforced the paradox. Photometric redshifts placed these galaxies at the correct early epoch. Stellar population models confirmed unexpectedly old ages. Morphological analysis confirmed structure where none should exist. Signal-to-noise ratios were sufficient to rule out statistical noise. Independent teams and instruments produced consistent results. The early universe was populated by galaxies that were simultaneously too old, too faint, and too structured. Even subtle details contributed to the sense of impossibility. Some galaxies displayed evidence of star formation concentrated in small knots, separated by diffuse regions, suggesting internal regulation of star formation processes. Others showed slight elongation along one axis, implying rotational motion, perhaps hinting at nascent disks. These faint structures were visible only because of Hubble's extraordinary sensitivity and long exposures, yet their mere presence indicated that the universe had begun organising itself with surprising sophistication very early on. Astronomers stared at these results in disbelief and excitement. The combination of age, metallicity, and structure in these faint galaxies formed a puzzle that standard cosmology could not solve. How could stars form and evolve so quickly? How could galaxies develop internal organization in a time when theory predicted only random clumps? Each photon in these faint structures carried evidence of accelerated evolution, a cosmic cheat sheet that contradicted every model of the early universe. Ruling out everything else. When the initial images were analysed, the excitement was immediate. Galaxies that were too many, too old, and too structured appeared where none should have existed. But scientists are trained to question everything. Extraordinary claims require extraordinary scrutiny. Could there be another explanation? Was it possible that Hubble wasn't seeing the universe as it truly was? Could these impossible galaxies be illusions created by dust, gravitational lensing, or a subtle problem with the instruments themselves? Dust is the first suspect in any cosmic puzzle. Interstellar dust absorbs and scatters light, and its presence can make distant galaxies appear fainter or redder than they actually are. The effect is well understood, described by extinction curves that predict exactly how dust changes the colour and brightness of light across wavelengths. If the early universe had a hidden dust layer along the line of sight, it could, in principle, mimic some of the observed anomalies. But the Hubble Deep Field team knew the science too well to be fooled. Models of dust absorption were applied immediately. These models account for the expected distribution of dust both in the Milky Way and in intervening galaxies. In these models, dust reddens light in a predictable way, more strongly at shorter wavelengths. Astronomers compared the observed colours of the faint galaxies across optical and infrared filters to the predictions from these dust models. The differences were stark. Dust would have altered the colours gradually, creating smooth reddening. The observed anomalies, however, were inconsistent with this pattern. Some galaxies were bluer than expected, some redder, and the variation was irregular, not smooth. Dust alone could not explain the range or structure of the colours. Infrared observations provided another test. Dust emits infrared radiation and can obscure optical light while still letting infrared photons pass through. Hubble's JWST infrared camera allowed astronomers to cross-check the suspected dust influence. If dust had been responsible for the observed faintness or structure, the galaxies should have appeared differently in infrared. Yet the infrared images matched the optical patterns closely. The same number of galaxies appeared, the same structures were visible, and the same colour anomalies persisted. The evidence from infrared directly contradicted the dust hypothesis. Extinction curves were examined in detail. Every galaxy's light was tested against known absorption laws. The team considered both Milky Way-type dust and dust with properties expected in early galaxies. None of the standard curves could reproduce the observations. Dust might hide a galaxy or make it appear fainter, but it cannot create the number of galaxies observed, nor produce the structured morphologies revealed in the images. The distribution of light within each galaxy, the disk-like shapes, the clumps of star formation, all of these features were incompatible with the dust explanation. After dust was ruled out, gravitational lensing became the next candidate. Gravitational lensing occurs when a massive foreground object bends the light from a more distant source. Lensing can magnify, distort, or multiply the images of background galaxies. In principle, a foreground mass could produce apparent overdensities, making a normal patch of the universe look crowded with galaxies. Strong lensing produces arcs, rings, or multiple images of the same source. Weak lensing subtly distorts galaxy shapes and orientations. Either effect could, in theory, create the illusion of impossible galaxies. Hubble's data, however, told a different story. Careful mass mapping of the field showed no massive objects along the line of sight. Galaxy surveys in the foreground, including spectroscopic redshifts and wide-field imaging, detected nothing capable of producing significant lensing effects. There were no massive clusters, no concentrations of dark matter inferred from weak lensing patterns, no hints of gravitational potential that could bend light at the scale required. Distortion patterns, the hallmark of lensing, were also absent. In strong lensing, arcs and multiple images would be obvious even in faint galaxies. Weak lensing would produce subtle alignments of galaxy shapes along preferred axes. Neither was present. The faint galaxies in the field retained random orientations and shapes, except for the internal structures intrinsic to the galaxies themselves. There was no coherent shear across the field, no alignment suggesting that light had been warped by an unseen mass. Mass estimates reinforced the conclusion. Calculations of the amount of dark matter or foreground mass required to reproduce the observed galaxy density revealed an impossible scenario. There simply was not enough matter in the line of sight to generate the effect. To explain the observations through lensing alone, the foreground mass would need to be greater than anything detected in similar patches of the universe. Every measurement contradicted the lensing hypothesis. With dust and lensing eliminated, the team turned to the instruments themselves. Could WFPC2 ACS or WFC3 be producing artifacts? Could long exposure stacking, readout electronics, or subtle calibration issues have generated false galaxies? The first step was independent reprocessing. Raw data from the deep field exposures were sent through different software pipelines developed by separate teams. Each pipeline used distinct algorithms for cosmic ray removal, dark current subtraction, flat field correction, and stacking alignment. The results were identical. Faint galaxies persisted in the same positions, with the same structures across all pipelines. Cosmic rays and hot pixels were eliminated in each reprocessing step. Exposure stacking was carefully verified. There was no evidence that the procedures themselves had introduced false signals. Parallel fields were analysed as a further check. Hubble had previously observed similar empty patches using the same instruments. These fields, processed with identical techniques, did not reveal comparable anomalies. Noise levels, photon counts, and faint galaxy distributions match predictions from simulations in those fields. The contrast between the impossible field and parallel observations confirmed that the effect was real, not an artifact of instruments or processing. Repeat observations added additional confidence. Hubble revisited the patch over months and years, sometimes with different instruments, sometimes with different observing strategies. The faint galaxies, the structures, the colours, and the unexpected counts remained consistent. Exposure times varied, orientations changed, detectors were swapped, yet the results were reproducible. Independent teams within the Hubble collaboration confirmed the findings. There was no instrument-induced illusion. Even peer review failed to uncover hidden errors. The data were shared with external experts who examined every aspect: instrument calibration, reduction pipelines, cosmic ray mitigation, exposure stacking, and statistical analysis. Every reviewer concluded the same: the faint galaxies were real, the structures were real, and the anomalies could not be explained by dust, lensing, or instrumentation. This process of elimination was rigorous because extraordinary claims demand it. Every possible explanation for spurious results, foreground contamination, dust absorption, lensing magnification, detector errors, or image processing artifacts, was examined, modelled, tested, and ruled out. Every photon, every smudge, every faint structure had been verified multiple times. Every alternative hypothesis had failed. The universe itself was leaving no alternative. Hubble's deep stare had uncovered something that was not an artifact of the telescope, not an illusion created by matter along the line of sight, not a trick of the light. The faint galaxies, with their number, age and structure, were real. The instruments were accurate. The data were solid. The anomalies persisted, independent of any conceivable observational bias. In the absence of dust, lensing and instrument error, the impossibility remained unchallenged. The galaxies were too many, too old, too structured, and their abundance and properties simply did not match the predictions of the standard cosmological framework. The careful, methodical process of ruling out every alternative made the universe's contradiction even more stark. What Hubble had revealed could not be explained away by ordinary means. What this broke in cosmology. When the data finally sank in, astronomers realized that the universe, as they thought they knew it, was in trouble. The galaxies Hubble had revealed were not just anomalies. They were full-scale contradictions to the models that had shaped cosmology for decades. The hierarchical formation model, the backbone of galaxy formation theory, was under siege. According to this model, small structures collapse first, merging gradually over billions of years to form larger galaxies. Galaxies should grow slowly, piece by piece, building complexity over cosmic time. But the deep field images told a different story. In the patch of sky that Hubble had chosen, galaxies were already numerous, already old, and already organized, far earlier than the models allowed. Hierarchical formation predicted that galaxies in the first billion years after the Big Bang should be rare, small, and irregular. They should resemble loose clumps of stars, with star formation scattered chaotically across diffuse clouds of gas. Instead, Hubble revealed disk-like shapes, clumps of star-forming regions, and mature stellar populations. The early universe had been assembling galaxies not slowly and gradually, but with startling speed and efficiency. Cold dark matter, another pillar of cosmology, was part of the problem. The lambda CDM model assumes that dark matter dominates the gravitational landscape, forming invisible halos that pull gas together to create galaxies. The density of dark matter, its distribution, and its collapse rate all dictate how fast galaxies can grow. According to simulations, dark matter halos at these redshifts should have been small, scattered, and just beginning to merge. Yet the number of galaxies observed required halos that were already massive and concentrated. Gravity, it seemed, had been more efficient than the models predicted. This raised immediate questions about the assumptions underlying galaxy formation. How fast could halos collapse? How quickly could gas cool and condense into stars? What processes regulate star formation in the first billion years of the universe? Every parameter used in simulations, dark matter density, halo growth rate, star formation efficiency, was suddenly suspect. The universe had forced theorists to re-examine assumptions they had long considered reliable. The dark matter problem deepened with every calculation. To account for the observed number of galaxies, the required density of dark matter had to be higher than expected. Halo growth rates implied that massive concentrations of matter must have formed extremely quickly, in a fraction of the time allowed by standard models. Without these dense halos, galaxies could not have formed so early. Simulations run with conventional parameters failed to reproduce the observed galaxy counts. The mass simply wasn't there. The missing mass problem, already a known challenge in cosmology, had just become far worse. Simulations had to be adjusted to make sense of the data. Dark matter halos had to grow faster, sometimes at rates previously thought impossible. Feedback processes, how stars heat surrounding gas and regulate star formation, had to be less effective, or galaxies would not have formed so quickly. Gas cooling had to be faster than predicted. Every change pushed the models to extreme conditions, almost bending the rules that had been considered standard. Even then, simulations often fell short, unable to reproduce both the number and structure of the galaxies simultaneously. Star formation, it turned out, had to begin earlier than anyone had thought. To explain the old stellar populations observed, the first stars, population 3 stars, must have formed within the first few 100 million years after the Big Bang. These stars would have been massive, short-lived, and efficient at producing heavy elements that later generations of stars could inherit. Yet even with early population 3 stars, the sheer abundance and organization of the galaxies required sustained, intense star formation over hundreds of millions of years. Feedback mechanisms, which normally regulate how fast stars form by heating and dispersing gas, appeared to be failing. Galaxies were forming stars rapidly, efficiently, and consistently across a patch of the universe that should have been sparse and chaotic. Gas cooling, a fundamental process in galaxy formation, had to be reconsidered. In order for gas to condense into stars so quickly, it must have lost heat at a much faster rate than standard physics predicts. Cooling allows gas clouds to contract under gravity and ignite nuclear fusion, but at these early times, the universe was still hot, filled with energetic radiation. Yet the galaxies in the deep field showed that gas had already cooled, settled, and formed stars in dense clumps. The timing of cosmic cooling, long considered well understood, now had to be rewritten. The consequences for cosmology were immense. If galaxies could form this quickly, the timeline for structure formation across the universe might need adjustment. Hierarchical assembly might have occurred faster everywhere, not just in this small patch. Dark matter's role in shaping galaxies had to be rethought, and the properties of the first stars had to be reconsidered. Even the standard measures of cosmic density and expansion could be affected, since these calculations depend on assumptions about when and how galaxies formed. Every observation reinforced the puzzle. Galaxies that were too many, too bright, too old, and too structured all pointed to the same conclusion. The early universe was far more active and efficient than theory allowed. This wasn't a subtle discrepancy. It was a systemic challenge to the models that had shaped cosmology for decades. Every parameter, halo mass, gas cooling rate, star formation efficiency, dark matter distribution, was suddenly uncertain. The collision with galaxy formation theory became unavoidable. Simulations designed to reproduce the early universe, run with the best understanding of dark matter, baryons, and feedback processes, could not produce the Hubble deep field. The models predicted fewer galaxies, later star formation, more irregular morphologies, and lower metallicity. Hubble revealed a universe that had sprinted ahead of the models, forming stars and galaxies with a speed, efficiency, and order that was impossible to reconcile without radical changes. The dark matter problem grew with every calculation. To match the observed abundance of galaxies, halos had to form faster and be more massive than expected. The required densities were higher than what lambda CDM predicts at these redshifts. The missing mass implied that either dark matter behaves differently than theorized, or that additional physics must be included in models to accelerate halo collapse. Simulations that ignored these constraints failed spectacularly, producing universes far less populated than Hubble had revealed. Star formation timelines were compressed dramatically. Instead of a gradual build-up, the first generations of stars had to ignite almost immediately after the universe became transparent. Population 3 stars had to exist in greater numbers, forming dense clusters that enriched the gas with metals more quickly than previously thought. Feedback mechanisms, which normally slow star formation by heating and dispersing gas, could not have been as effective. Gas had to cool rapidly, collapsing into stars with a speed that standard physics struggles to explain. The implications touched every corner of cosmology. The early universe was no longer a quiet, slowly evolving landscape. It was active, crowded, and astonishingly efficient at producing galaxies. Dark matter models, star formation theories, and galaxy assembly timelines all required urgent re-evaluation. The Hubble Deep Field was not merely showing faint, distant objects. It was exposing the limits of our understanding of how the cosmos grew from simplicity into complexity. In every sense, Hubble's deep stare had forced a collision. Observations clashed with theory, models conflicted with reality, and assumptions that had seemed solid for decades now looked fragile. Galaxies formed faster, denser, and more organized than predicted. Dark matter halos had grown too quickly, star formation had ignited too early, and feedback mechanisms had failed to regulate it. Gas cooling had proceeded at impossible speeds. The early universe, once imagined as a quiet and empty expanse, was instead crowded with life, stellar life, and structured in ways that left cosmologists scrambling for explanations. Confirmation from other telescopes. Hubble had already shaken the foundations of cosmology. Galaxies too many, too old, and too structured appeared in a patch of sky where theory said none should exist. But skeptics demanded proof beyond a single telescope. Could these discoveries be replicated? Could independent instruments operating on entirely different principles confirm that what Hubble had seen was real? The universe was about to provide multiple confirmations, each one more astonishing than the last. Ground-based observatories were the first to join the investigation. Telescopes like the Very Large Telescope in Chile, Keck in Hawaii, and Subaru in Japan turned their enormous mirrors toward the deep field. Unlike Hubble, these instruments are affected by Earth's atmosphere, but they have their own advantages: massive light-gathering power, spectroscopic capabilities, and flexibility across multiple instruments. With months of careful planning, astronomers aimed to verify the galaxies Hubble had revealed. Spectroscopy became the key tool. While Hubble's imaging shows galaxies as faint smudges of light, spectroscopy splits that light into its constituent wavelengths. It allows astronomers to measure redshifts, confirm distances, and even detect chemical signatures. Ground-based teams spent nights aligning instruments with the exact coordinates of the deep-field galaxies, sometimes exposing their detectors for hours to collect enough photons from these faint objects. The first spectra were dim, noisy, and barely distinguishable from the sky background, yet even the faintest emission lines told a story. Redshifts matched Hubble's predictions. Galaxies that had appeared at the edge of detection in Hubble images were confirmed to be billions of light-years away. The signal-to-noise ratios were lower than Hubble's, but the independent confirmation was undeniable. These galaxies were not foreground flukes or misidentified stars. They were distant, ancient galaxies whose light had travelled nearly the age of the universe itself. Emission lines added another layer of confirmation. The presence of hydrogen alpha, oxygen, and other nebular lines indicated ongoing star formation. Even in galaxies that appeared faint and red in Hubble images, these emission lines revealed pockets of activity. The galaxies were alive with stars being born, just as Hubble's infrared observation suggested. Ground-based telescopes not only confirmed their existence, but also provided the first independent insight into their internal processes. Infrared observations with the Spitzer Space Telescope strengthened the picture. Spitzer could observe light at longer wavelengths, less affected by cosmic redshift, and detect the heat emitted by stars and surrounding dust. Some of the early galaxies showed an infrared excess, a glow that suggested substantial star formation hidden behind faint clouds of gas. The data allowed astronomers to estimate stellar mass more accurately. Many galaxies turned out to be more massive than Hubble alone had indicated, reinforcing the paradox. Not only were they numerous, old, and structured, They also contained far more stars than models predicted for their epoch. Spitzer helped rule out alternative explanations as well. If the anomalies seen by Hubble had been caused by dust obscuring or reddening galaxies, Spitzer's infrared data would have shown dramatically different fluxes. Instead, the infrared observations aligned with Hubble's measurements, confirming that the galaxies were intrinsically luminous and real. Dust might obscure some regions, but it could not create the number, age, or structure of galaxies observed. The consistency between optical, near-infrared, and mid-infrared data left little room for doubt. Then came the game changer, the James Webb Space Telescope. Hubble had glimpsed the early universe, but JWST had the resolution, sensitivity, and wavelength coverage to look deeper than ever before. Where Hubble had captured faint, diffuse smudges, JWST revealed astonishing detail, individual clumps of star formation, disk-like structures, and galaxies even farther away than Hubble had detected. JWST did not just confirm Hubble's findings, it expanded them. Spectroscopy with JWST transformed the field. Using its near-infrared spectrographs, astronomers measured precise redshifts for dozens of the previously mysterious galaxies. Some were even more ancient than initial Hubble estimates, their light originating less than 400 million years after the Big Bang. JWST's instruments could detect the subtle fingerprints of elements, revealing that these galaxies had already undergone chemical evolution. The universe was older than expected, and its galaxies were more developed than theory allowed. JWST also found galaxies that Hubble had completely missed. The new telescope's infrared sensitivity uncovered faint, small galaxies hiding behind the cosmic glare, some of them even older than the galaxies that had first drawn attention. This confirmed that Hubble had not been wrong. It had simply observed the universe earlier in the detection frontier. The deep field was crowded with objects beyond Hubble's capabilities, demonstrating that the early universe was both abundant and surprisingly mature. The combination of ground-based spectroscopy, Spitzer infrared measurements, and JWST's high-resolution imaging created a compelling picture. Independent instruments, operating in different wavelengths and using different techniques, all told the same story. The impossible galaxies were not illusions or artifacts. They were real, numerous, old, structured, and massive. Each telescope added a layer of confirmation, turning what had once been a shocking anomaly into a reproducible, verifiable phenomenon. The implications were dramatic. The galaxies confirmed by other telescopes not only matched Hubble's counts, but also reinforced the challenges to cosmology. Hierarchical formation models, dark matter expectations, and star formation timelines were all pushed further out of line. The early universe was more efficient, more organized, and more crowded than any theory had predicted. Each photon confirmed by a separate telescope deepened the paradox. Ground-based follow-ups also helped map the spatial distribution of these galaxies. Observatories with wide fields confirmed that the patch Hubble had observed was not an isolated anomaly. Similar concentrations appeared in adjacent regions, hinting at a broader pattern of unexpectedly fast and efficient structure formation. JWST extended this mapping, revealing a rich web of galaxies stretching across previously invisible cosmic filaments. The early universe, once imagined as sparse and uniform, was revealed as a complex, structured network already in place. Infrared data continued to challenge assumptions. The balance between light absorbed by dust and light emitted by stars indicated high star formation rates in nearly every confirmed galaxy. Mass estimates increased, showing that even small, faint objects contained more stellar material than expected. Feedback mechanisms, gas cooling rates, and early star formation efficiency all had to be reconsidered in light of these confirmations. The universe had been building galaxies at an astonishing pace, and the evidence was coming from multiple independent telescopes. JWST also revealed details about the internal composition of these early galaxies. Clumps of star formation, concentrations of older stars, and chemical fingerprints showed that these galaxies had already undergone multiple generations of star formation. Some displayed hints of rotation, suggesting nascent disk formation far earlier than previously thought possible. Hubble had hinted at structure, but JWST made it undeniable, confirming that galaxy assembly in the early universe was both rapid and surprisingly ordered. Even the oldest galaxies were confirmed across instruments. Spectroscopic redshifts from ground-based telescopes matched Hubble's photometric estimates, while JWST refined these measurements to reveal galaxies whose stars were almost as old as the universe itself. The confirmation across optical, near-infrared, and mid-infrared wavelengths left no doubt. The early universe was far more mature than theory predicted. Together, these observations created a chain of evidence that was impossible to dismiss. Hubble had revealed the impossible. Ground-based telescopes had confirmed the distance and star formation. Spitzer had verified the mass and infrared properties. JWST had expanded the view, adding resolution, spectroscopy, and even older galaxies. Each instrument told the same story from a different angle, strengthening the case that the anomalies were real, reproducible, and representative of the early universe as it actually was. The scientific community watched as the deep field transformed from an anomaly to a confirmed phenomenon. Every independent observation reinforced the reality of galaxies that were too many, too old, too bright, and too structured. Cosmology could no longer ignore them. The universe that Hubble had glimpsed, already mature and organized, was now undeniable thanks to multiple confirmations across the electromagnetic spectrum and independent telescopes. In this era of cross-verification, Hubble's early findings were vindicated. The telescope had not erred. It had been first to peer into this patch of darkness. Every follow-up, every spectroscopic measurement, every infrared detection, and every high-resolution image from JWST confirmed that the deep field was real, and the early universe was far more active than theory had predicted. The impossible galaxies were no longer just a Hubble curiosity. They were a cosmic reality, confirmed across the world and beyond Earth's atmosphere. What we now know for sure. The Hubble deep field had shattered expectations, and subsequent observations only made the picture clearer. The universe was not taking its time. In the first billion years after the Big Bang, galaxies were forming faster, stars were igniting earlier, and cosmic structures were already remarkably organized. This was not a subtle difference in speed or density. The early universe had been building with an efficiency that no standard model had predicted. Astronomers quickly realized that timelines for galaxy formation needed revision. Previously, simulations assumed a gradual, step-by-step process. Small, dark matter, halos collapse first. Gas slowly cools. Stars form sporadically, and galaxies assemble over hundreds of millions of years. But the galaxies in the deep field told a different story. Massive halos must have formed almost immediately. Gas had to cool faster, and star formation had to ignite earlier and proceed at astonishing rates. The universe had been racing from the very beginning. Revised timelines began with the first stars, the population 3 generation. These massive, short-lived stars would have ignited within a few 100 million years after the Big Bang. They produced the first heavy elements, setting the stage for the galaxies Hubble and JWST now revealed. Instead of a slow trickle of star formation, these early stars must have initiated rapid cycles, enriching their surroundings and allowing subsequent generations of stars to form more efficiently. The deep field galaxies bore the fingerprints of these early, intense bursts. Star formation efficiency was higher than models allowed. Normally, gas in early galaxies would be heated and dispersed by radiation and supernovae, slowing further star formation. Yet the faint, structured galaxies in the deep field showed dense clumps of star formation, indicating that feedback mechanisms were less effective than predicted. Gas cooled and collapsed quickly, forming stars in concentrated regions. The early universe was not only forming stars, it was forming them in an organized, efficient manner that models had not anticipated. New baseline models began to emerge. Cosmologists had to recalibrate simulations to account for faster halo growth, earlier star formation, and more efficient gas cooling. Dark matter distribution, feedback rates, and baryonic processes were all adjusted to produce a universe that could match Hubble's observations. The baseline for early galaxy formation was no longer gradual assembly. It was accelerated, organized, and efficient, a radical departure from decades of theoretical expectations. One of the most striking revelations was that empty space isn't truly empty. Hubble's deep field showed that even the darkest patches of sky were teeming with faint galaxies, revealing the cosmic web in greater detail. Filamentary structures connecting galaxies, once imagined as diffuse and difficult to detect, were now visible. Matter was distributed along these filaments, shaping the universe in patterns that simulations had only hinted at. Dark gaps were never really empty. They were populated by faint, distant galaxies, a hidden infrastructure that only long, deep exposures could reveal. This realization also exposed biases in observation methods. Astronomers had assumed that faint patches of sky corresponded to emptiness, but the universe had been hiding activity in plain sight. Only by pushing instruments to their limits, through long exposures, stacking techniques, and infrared observations, did the underlying structures become apparent. The empty universe was, in fact, a dense and complex environment, alive with faint galaxies weaving through the cosmic web. Simulation updates followed rapidly. Cosmologists began tuning parameters for dark matter halo growth, gas cooling efficiency, star formation rates, and feedback suppression. Models were adjusted to reproduce the number, distribution, and internal structures of early galaxies. Parameter ranges were expanded to account for the accelerated pace of galaxy assembly. Even with these adjustments, reproducing both the density and structure observed in the deep field remained a challenge, highlighting open problems in understanding early cosmic evolution. Despite these updates, several mysteries persist. How did halos collapse so quickly without violating other constraints? Why did feedback mechanisms fail to slow star formation in these early galaxies? How do we reconcile the accelerated timelines with the overall expansion history of the universe? Every new observation opens more questions, revealing gaps in understanding that challenge even the most sophisticated simulations. Hubble and JWST together have established that the early universe was highly efficient in building structures. Galaxies form faster, star formation ignited earlier, and the cosmic web was already in place. Dark patches were never truly empty, and early structures were far more organized than simulations had predicted. The result is a universe that is dynamic, active, and surprisingly mature from its earliest moments, forcing astronomers to rethink timelines, processes, and assumptions about the first billion years of cosmic history. The universe's acceleration in building complexity is now the new baseline. Every subsequent study begins with the knowledge that stars, galaxies, and filaments formed rapidly, efficiently, and with unexpected organization. Models and simulations will continue to evolve, but the data from Hubble, Spitzer, ground-based telescopes, and JWST have established an undeniable truth. The early universe was far more alive than anyone imagined, and astronomers are still racing to catch up with what it reveals. why future deep fields will look different. Astronomers are learning fast from Hubble, Spitzer and JWST. The deep fields that revealed the impossible galaxies have changed the way scientists plan observations. Future deep fields will not be random patches of empty sky anymore. Targeting strategies are now designed to maximize what can be learned about the early universe, pushing deeper, wider, and in ways that combine multiple instruments and wavelengths. One major shift is synergy between telescopes. JWST provides unprecedented infrared sensitivity, detecting the faintest, reddest galaxies from the first few 100 million years after the Big Bang. The upcoming Nancy Grace Roman Space Telescope will complement JWST by surveying large patches of sky with high resolution, mapping hundreds of thousands of galaxies in the early universe. By combining the deep, narrow view of JWST with the wide, shallow surveys of Roman, astronomers can now study both the rare, massive galaxies and the faint, numerous population that was previously hidden. Survey redesigns are also underway. Instead of focusing solely on visually empty patches, astronomers are targeting regions with minimal foreground interference, low zodiacal light, and well-calibrated instrument conditions, but also fields likely to reveal new surprises. Statistical models now incorporate lessons from Hubble's impossible patch, predicting where early structures might be dense, where filaments could be detected, and where ancient galaxies are most likely to cluster. Observing time is precious, and future deep fields are being chosen not just for their emptiness, but for their potential to challenge and rewrite models again. These changes are already altering our understanding of the first billion years. The timing of cosmic reionization, the period when the first stars and galaxies ionized the neutral hydrogen in the universe, is being updated. The early galaxies Hubble revealed were far brighter and more numerous than expected, implying that the universe's energy budget during reionization was larger than models predicted. More photons were being emitted, more stars were forming, and the intergalactic medium was being lit up earlier than anticipated. The first billion years were not a dim, gradual awakening of the cosmos. They were a surprisingly bright and active period. Early universe brightness also affects interpretations of galaxy evolution. With more light being produced earlier, the formation and growth of structures must be reconsidered. Gas cooling, star formation, and chemical enrichment all happened faster. Energy budgets now account for higher rates of star formation, and simulations are being updated to reflect this accelerated activity. The deep fields have forced a re-evaluation of how quickly the universe went from simplicity to the complex cosmic web observed today. The next impossible patch of space is already being sought. Astronomers are scanning coordinates predicted by updated models, looking for regions that should be sparse but may hide hidden richness. By carefully analyzing cosmic variance, background noise and statistical probabilities, researchers identify fields most likely to contain galaxies that defy expectations. They expect to encounter new anomalies, galaxies that are too old, too dense, or too structured, because the Hubble patch was never a one-off fluke. The universe, it seems, has been consistently efficient in building structures across space. In planning these future fields, astronomers are also improving methods for detecting and analyzing faint galaxies. Exposure times are optimized, filters are chosen to maximize signal in key wavelength ranges, and stacking techniques are refined to reduce noise. With JWST and Roman working in tandem, astronomers can cross-check every detection, ensuring that the faintest, earliest galaxies are real and not artifacts. This new level of precision will reveal the universe in ways Hubble could only hint at, producing deep fields that are not just images, but rich datasets of cosmic evolution. Every new field has the potential to break assumptions again. If Hubble's impossible patch was the first clue, the next fields will expand the scope of the mystery. Observations may reveal clusters of galaxies forming earlier than predicted, more structured disks, or galaxies with unexpectedly high mass for their age. Each discovery will feed back into models, forcing constant revision. Deep fields are no longer just exercises in observation. They are experiments in challenging what we think we know about the cosmos. Ultimately, future deep fields will look different because astronomers now know what to look for. They will combine the power of multiple telescopes, select regions strategically, and use sophisticated models to predict where the universe is likely to surprise us next. These fields will show that the early universe was brighter, busier, and more structured than imagined, mapping the cosmic web in unprecedented detail. They will confirm that the impossible galaxies Hubble found were just the beginning, and that the early universe still has secrets waiting to be revealed.